Hey, welcome to your first lesson in the first training on Low Level Academy, Zero to Hero C Programmer. Now, what is this course about? This course is going to be, as the name implies, a Zero to Hero course that takes a beginner programmer with no knowledge in C to a master C programmer. Now, you're probably wondering, why would I take this course instead of the other hundreds of courses that are on YouTube? I've been writing in C for over 15 years at this point, so I have experience and I love to teach. But also, I find a lot of the courses online that already exist in C don't do project-based learning. It's kind of, you write some toy code, you write a hello world, you use a string here, you use a heap there, but none of the training is holistic, where you actually build a thing. And that's where I find a lot of the experience comes from that makes you a good programmer. Coming up with an idea, figuring out how to design that idea, and then writing that idea in code. That design process creates problems that exposes you to issues that make you a better programmer. Now, the project we're going to be doing in this course is fairly simple, but it teaches the fundamentals of the C programming language. We are going to do a file-based database that uses structures and file input and output to store some information of variable length to the disk. And then in later courses on this platform, we'll take that database service that we use as a file service and attach a networking stack to it and a thread-safe thread pool to it, so that combined we have a holistic project that makes use of multiple parts of the POSIX API. And if you don't know what any of that means, that's totally fine. I guarantee you by the end of this course, you will know what that means and be confident in your programming skills. Now, you're probably wondering, is this course for me? Do I have enough experience to take this course? And the answer is most likely yes. If you have done any programming in any language at all, then you're qualified for this course. You don't have to have a huge amount of experience. You actually can have zero experience in C to take this course. If you want to learn how to write C, how to go from being a zero to being a hero at the C programming language, and how to write bigger scalable projects in this language, then this course is for you, and thank you for signing up. We'll see you in the next lesson. Hey guys, welcome back to your next lesson in Zero to Hero C Programming. This one has a little less to do with programming itself and more on the pace that you take this course and kind of how to set mini goals and to keep motivation up while you're taking a longer course, learning a new language that may be harder for some people. This is especially important for new programmers, as I think it's really easy to get overwhelmed and maybe even feel like you know a concept early on, but then go to recall that concept later on in a course and be like, oh, I forgot that syntax. So then your entire foundation kind of breaks down. Really, really important that instead of setting this mega goal that, oh, by the end of the month, I'm going to be a master of C programming, instead break that down into mini goals where instead of, trying to master C in this giant gulp, break it down into smaller parts. The mini goal could be, this week, I'm going to understand structures. And then this week, I'm going to understand pointers. Take this course slow, maybe 1 or 2 sections a week. And every time you take a new section, wait a day. And then that next day, write a little bit of code. That will ensure 2 things. 1, that you actually understand the lesson after learning the information directly. And then also 2, that information will get stored into long-term memory so that later on in your life or later on in the course, you can actually recall it. Doing this will allow you to actually, A, have confidence that you know the material because you were able to take a lesson at one time and then recall it later on, but then also it'll keep your foundation solid so that when we get to module 12 in the course, when we actually start writing a really big project, you will know all of the information in the modules and not have to go and look back at every module every time we go to use the heap or go to use a structure. So again, take this course slowly, do 1 or 2 sections a week, and then later on in that week, make sure you're writing code to confirm in your head that you actually know the information. So that's it for this one. We'll see you in the next lesson. Keep going. Hey guys, welcome back to another episode of Low Level Academy. Today we're talking about the tools we're going to use in this course and how to get those tools all set up before we get moving and actually starting to write some code. So here I am in an Ubuntu 2204 long-term support VM. And we're going to use the kind of the default setup and kind of show you how to go from the default setup to a place where you can start writing and editing code. You'll see later on in the course that I use Vim and kind of my own personal setup. You don't have to do that if you don't want to. This, what I'm going to show you here, is the minimalist setup where you can go from a fresh Ubuntu install to a place where you're writing code nice and easy without being over inundated with tooling, right? I know a lot of people typically like to use NeoVim or Vim and kind of really spend a lot of time configuring that text editor to be the way that they want it. And that's probably a good use of your time if you're more of a senior or, a principal level dev. But for this, we're going to use a basic text editor, Sublime Text. We're going to use the basic default terminal. and do stuff in there. I think it's the best way to learn without getting kind of overwhelmed with tooling and spending too much time configuring your tooling. So to start out, all we're gonna do is run sudo apt update, make sure that all of our repos are updated in apt. Apt, if you don't know, is a package manager in Ubuntu that allows you to install things from the Ubuntu package repo, and that's what's happening here. It's updating all the repos. And then from there, we'll do sudo apt install, do gcc, and build essential. This is just gonna make sure we have all the things we need on the computer to be able to build tools. So I already have this. This may prompt you to press yes, and then you press yes, and go from there. And you'll know that we can run the rest of the course if when we type gcc, we get this error, and if we type ld, we get this error, and if we type make, we get this error. If all these things happen and you don't get a cannot find gcc ld whatever, then we are good to go. Next, we're gonna install Sublime Text. So I'll put the link in the description for the course down at the bottom. We're gonna go to the Sublime Text website. We need to install the GPG key of Sublime Text so that we can actually install packages from it. We do that by running that command there. And then from there, we have to include the package repo in our Ubuntu package repo list. And we do that by running this command here. Copy and paste, pretty straightforward. And then we have to do another sudo apt get update, or we'll just do sudo apt update because we're not using apt get, we're using apt. They're actually two separate programs. So you see here that we actually included Ubuntu's Sublime Text distro in there for apt stable. And now we can just go ahead and use apt to install Sublime Text. Sudo apt install Sublime Text. There we go. Now it's installing it. We couldn't have done that before because we didn't have this repo in our apt. Give that a second. There we go. And then to run Sublime Text, we do subl, S-U-B-L. And there you go. From there, now we have a fresh install with Sublime. We can kind of blow this up a little bit and we can start to type a little bit of code that we'll do later on in the future. So again, if you want to configure your environment to do more, to have more stuff, if you're more comfortable with Vim or maybe NeoVim or Atom or whatever, feel free to do that. This is just what I recommend for people that are learning to code because I think Vim is complicated for people that are learning to code fresh. So, you have to learn all the keystrokes and it gets very complicated to use Vim. So I'd like to have a simple terminal with the basic tools, and then you have Sublime Text over here where you can write your code, and then you can go from there. So there you go. Continue to customize if you'd like to, and we'll see you in the next lesson. See you there. Okay, so here we go. This is the fun part of the course that we will have access to after module 12. The beginning 11 modules are kind of like an intro to the C language with examples to write as we go along. But then module 12 is where we actually start to take all of those, add them together, and build our final project. So this is a project that we're building towards. And as you're going through the lessons, figure out how you think each of the things that you're learning, like structures, pointers, the heap, could fit into this project. And obviously I'll explain it to you when we get there, but it's good to get your mind primed for that. So this is the Zero2Hero database project. A simple idea, but it'll actually flex a lot of the muscles of the C language to make this possible. We're going to create an employee database that will take a file that is a database structure and allow us to add, update, store, and search. So add, update, store, and search employee information. And the information is going to be an employee structure that is the name of the employee, their address, their hours worked, and maybe we can write it so that we can add additional information to that structure as our project grows. So we'll take a database file that we'll write, we'll come up with the spec for that file, we'll be able to add employees to that file, search through them, update them, do all this stuff, and then write that file to a disk. All of that's going to come together at the end of the course, so make sure you're thinking about how we can incorporate features in the C language to this database project. So we have come to the end of a section. So your homework for the end of the section for this week is to start thinking, how would you design an employee database? What would the different modules of the database be? And how would you use the features of the C language as you know them to design this system? And again, as we go through the course, maybe your assumptions will change, but thinking about that now ahead of time gets your mind ready for the rest of the course. So start thinking about that, and we'll see you in module 2. Hey guys, what is up? Welcome back to another lesson in Low Level Academy Zero to Hero C Programming. Today we're talking about what is the C programming language. It's probably good to understand a little bit about the history of the language and where it came from and where it is today and how we got here. So C is a general purpose programming language created by Dennis Ritchie at AT&T Bell Labs in 1972, meaning yes, the C programming language is over 50 years old. Now, while it's regarded today as a low-level language, it was actually thought of as a high-level language back in the time that it was created because it replaced a lot of the languages that were closer to the hardware and gave you a clean abstraction away from the CPU. Now, C was born out of two languages that were invented at Bell Labs, the first being ALGOL, or ALGOL, and the second being BCPL. ALGOL invented in 1960, and then BCPL in 1967. Because ALGOL started with A and BCPL started with B, Dennis Ritchie decided, yep, this language will be called the next letter in the alphabet, and hence we get C. Now, since 1972, there have been various forms of the C language, various standards that have come up through discussions amongst the C programming community. So originally, when C was released in 1972, the syntax and the formatting for a lot of things like function calls and variable declaration was different than modern C now. So first in 1972, we had the base C language, and then in 1978, we had what is called KNRC, another form of C. 11 years later, in 1989, what is known as ANSI C came out, and then 1 year later in 1990, C received an ISO certification. That's the International Standards Organization, and that helped create what is known today as C89 or C90. They both refer to the same language. Now, ISO standardization gave some general formatting changes to the language that made the language more scalable and accessible to a larger group of people. Now, since then, over the years, there have been incremental changes to the language that add certain features here and add different variable types there, but generally, C89 is known as the most standard form of C. Now, despite being 50 years old, the C programming language is still used literally everywhere in the world. The main reason that C survived this long is the amount of power that the C programming language gives you to do things on the computer. C gives you a ton of tools to give you control over the memory space of your program, to give you control flow that allows you to control how the program behaves based off of that memory, and access to the kernel API for the operating system that you're using. With all these tools together, you can make the C program do literally whatever you want. What are the pros and cons of learning C? Now, whether you're a first-time programmer, this is a first language that you're learning, or you've been learning to program for over a decade, there is significant value in learning C. But the C language does have some rough edges that make it difficult to learn if you're only used to languages like JavaScript or Python. C gives you the ability to do whatever you want. You get significant power when you write code in C. By writing in C, you create code that is human readable that gets translated directly down to machine code, and because of that, you have a lot of access to do kind of whatever you want. But with great power comes great responsibility, and learning to code in C will teach you that extremely quickly. If you make a mess, like you allocate from the heap, you have to clean it up, you have to free it. If you create a buffer for data to go into, you are responsible for making sure that that buffer is the correct size. No one is going to check that for you. When you go to put data in there, no one is going to check for you to make sure that that buffer is the right size. That's on you to figure that out. The C language doesn't have a garbage collector, which means that as you write code that uses the heap, if you don't free it yourself, your program will leak memory over time. Now, while it may be difficult and there are some rough edges that you will hit along the way, learning C will teach you how computers work at an extremely low level. And learning to code in C will actually make other languages easier for you to learn because you'll know under the hood what's going on. Learning to code in C will prepare you to learn other languages that are a little simpler like Python and JavaScript. So that's the C language at a high level. Go ahead and watch the next video. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programmer on Low Level Academy. Today we're talking about what is C compared to other languages. What makes C different than the rest of the landscape, and why would you choose C over these languages? Now, C is a really unique language in that when you write C code, you are writing human readable language that gets translated down directly to machine code. There's almost no middleware that gets injected. Over time, you'll actually get a sense of what blocks in C convert to what blocks in assembly. It is that direct of a translation. There's almost no middleware going on and no work being done by the compiler to make your code different. Now, there are some optimizations that happen, but overall, you are literally directly writing human code that goes into machine code. Now, when discussing programming languages, we typically talk about languages in the form of the following distinctions. Is this a compiled language or an interpreted language? Does this language have a garbage collector? Is the language strongly or weakly typed? And is the language memory safe? Now, C is a compiled language, which means that when you write this code, it gets compiled down to the machine code of the architecture that you're on. So when you write C code and you use the GCC compiler, you are turning your human readable source code into Intel opcodes that tell your processor what to do. And maybe if you're on an ARM device or you're on a MIPS device, it'll change depending on the architecture, but the code becomes the language of the computer. There's no middle layer that has to interpret it. You're literally telling the CPU exactly what to do. Because the language gets compiled down to machine code, it is typically regarded as fast compared to other languages like Java and Python that are interpreted language. Python, for example, is an interpreted scripting language where an interpreter at runtime reads your code and converts that to bytecode that gets ran by the interpreter. The interpreter itself is written in machine code that runs on the CPU, but your code actually never touches the CPU. It's getting interpreted by something else. C, being compiled, does not do that. It runs directly on the CPU. And similarly, Java is run in the Java virtual machine, meaning that an interpreter turns your Java class files into JVM bytecode, and that bytecode gets ran by a virtual machine that runs on top of your CPU. So the JVM is written in machine code, but your code is only ever put into bytecode. Okay, next, are we talking about a strongly or a weakly typed language? The topic of if C is strongly or weakly typed is kind of a holy war. There's really no official answer. I will fall back to what Dennis Ritchie said in that C is a loosely typed language or a weakly typed language for the following reason. A strongly typed language is a language that demands types at compile time and enforces those types as the program runs. And a weakly typed language is a language where you have a variable and its type can change over time. So for example, in Python here, I have variable x. X is set to 4, so its type is an integer. But then I can later on in the code say that x is a string. The reason why Dennis Ritchie said that C is a loosely typed language is because while the types are strong and defined at compile time, you can, as the program goes on, change how the compiler or how the program looks at those types. You can say that X is now going to be a void star, or X is now an int star, even though it started as a float, for example, right? So because we're able to make those distinctions at compile time, the argument was made that it is a loosely typed language and that types don't survive long as the program runs, therefore making it a weaker language on the typing side compared to languages like Rust. Next, does C have a garbage collector? No, C does not have a garbage collector. Now, there's kind of a pro and a con for this. So the pro of C not having a garbage collector is that it does not suffer from the overhead of running a garbage collector. Languages like Go that use a garbage collector do have performance overhead in tracking which memory is currently in use, which memory has gone out of scope with no tracks on it, and then having to run the garbage collection run to pull that memory back into the allocatable space. Now, the downfall of C not having a garbage collector, obviously, is that now the programmer is responsible for tracking which memory is and is not in use and freeing it as appropriate. If you fail to free your memory over time, your memory will be leaked out of the program and you could eventually exhaust the resources of the system, which is not good. And finally, is C memory safe? No. You will very quickly realize that C is not a memory safe language. What does it mean to be memory safe? So a memory safe language is a language that gives the programmer the ability to write code freely and not violate the bounds of the memory that they're given. So for example, if you have a buffer of memory in Rust, a memory safe language, if I try to index outside of that array, if I try to access memory that was not allocated to me, the Rust runtime will actually yell at me and say, hey, you can't do that. In C, as I'm sure a lot of you will figure out if you're new to programming, this is not the case. C will very easily let you access literally wherever you want if you make a simple logic error like an integer overflow or underflow when indexing into an array, for example. And again, if that's confusing to you, that's okay. We will get into that into a future video. And there we go. That's pretty much how C is different than other languages. So let's take it to the next level and see you in the next video. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming on LowLevelAcademy. Today we're talking about, is C still relevant? Like, should you be learning the C language? And obviously you're here, so you probably already have your opinion. But I think it's important to talk about because there are so many new languages that come out every day. There are so many new languages that come out all the time. And new programmers want to figure out, I only have so much time. You're probably a student either learning computer science or maybe even learning a different discipline, but you want to spend your extra free time to become a better programmer. And what language should you invest your time in? So is C worth my time? And to even exacerbate that, C is a 50-year-old language. So is it too old? Is C dead? Is there something else we should learn instead? Should I study one of the big ones like Rust? I hear all the time about how Rust is the future and Rust is memory safe. Or Go. Go has a garbage collector and is really easy to write good, clean code. Those are really good examples of new languages, but I want to emphasize the fact that while C is 50 years old, literally the entire world still runs on C. There is C in your operating system right now. There is C in the browser that you're watching this video on. There is C in the router at your house. There's C probably in your microwave. There's C literally all over the world. So while the C language is extremely old, The reason that C has stood the test of time is because of the power that it gives the developer. C allows you to literally do whatever you want, whenever you want. And while that has created some security vulnerabilities in certain stacks of software, looking at you, Microsoft, it has enabled the programmers over time to write code that survived the test of time and made it into basically every device we use today. This doesn't mean that things aren't changing, right? It is true that Rust is becoming more and more popular. Go is becoming more and more popular. So if you have additional free time, I would say learn those languages as well, because you don't want to be stuck in the past and only be a one-trick pony. But you want to have your foundation set and use C for two things. A, to stay relevant and be able to program against a language that is used literally everywhere. And then also you want to use C to teach yourself how computers work so you can take that knowledge and then go use it to learn a different language like Rust or Go. Also, a little fun fact, don't forget, things like COBOL, for example, a language that's used to program mainframes, still exist. And as the number of people who know how COBOL works goes down, the salary for those jobs goes up as well. For example, I think a COBOL engineer, if you work for the state of New Jersey, the government, they will pay you like $150,000 to go work for them because no one else knows how the language works. So there is some value also in knowing older languages as well. Now, C isn't that old. C is not COBOL level old. C is extremely relevant still, but I think it's an interesting analogy when you look at languages that are, supposedly dead, right? So with that said, let's move on to the next lesson, and we'll see you guys there. Hey guys, what is up? Welcome back. Welcome to your next lesson in Low Level Academy, Zero to Hero C Programmer. Today we're talking about variables and variables in the C language. Now, again, as we're taking this course, remember that we're trying to figure out how all these different parts apply to our person database project, the course project for this course. A variable in C is just a location where you put some kind of memory, right? You have some information that you want to use in your program. All a programming language does is store information and then do things with that information based on the values of that information. And where do we put this information? We put it in variables. So for example, if we are creating our personnel database and we wanted to store, for example, the ID, the number of a person, we would store that person's number in a variable. So to begin, the way you declare a variable in C, this is the generic format of how a variable declaration is written in C. So the part will be first the type of the variable, then the name of the variable, and then the equal sign, and then its initial value. This is going to be the way that we set up every variable declaration in the C language. This type will depend on the type of information that we want to supply to the variable. This name will be used to describe to us, the programmers, and also future programmers who may take on our work, what the point of that variable is, right? Why did we decide to make this variable? And then the initial value, right? This initial value can be a constant value, like a number like 5. It can be a string like my name, low level learning, or it can be an expression that uses other variables. Let's write a couple examples to figure out what we're talking about here. So one type that we can use to get you familiar with the C language is the integer type. An integer is used to store a number. The int type will be used like this, int, and you can see that my syntax highlighter here knows that int is a valid type, and I'm using nvim in case you were curious. Other things like Sublime or VS Code will also highlight the proper syntax. So it knows that int is a variable type in C. Now I'm going to say that my name for my variable is person ID, right? I need to have a descriptive name for the variable so that when I read this code later, I know what it does. I could name the variable P, or I could name it I, but making a descriptive variable name like person ID tells me what's going on in the code. And person ID is going to be set to an initial value of 0. I can also later make another variable called person2ID and say that its initial value is equal to, gonna move my fat head here, person ID plus 1. I can use an expression here to define another value that gets calculated at runtime. We also have other data types we'll talk about later on in different videos that can store different kinds of information, like a character, for example, that can store string information. We also have things like floats that store decimal values, and a bunch of others we'll cover later on in other videos. So guys, this is it. This is how we store variables in C. Continue on to the next video and figure out how we can use them. Continue on to the next video to figure out more about scope rules in C. Hey guys, what is up? Welcome back to your next lesson in LowLevelAcademy Zero to Hero C programming. Today we're talking about variable scope rules. We're going to talk about what variable scope actually means, the different levels of variable scope, and how that will affect your programs as you write them in the future. So variable scope is basically a definition of who is able to access variables you've defined, or where in your code you're able to access them. So for example, let's say we wrote our code here and we use the person ID variable. And later on, I want to actually update the person ID variable. I can say person ID plus equals 1. Well, there are a couple places in our code that we can do this and a couple places where we can't do this. Now, the location that we're able to run person ID plus equals 1 is a place where person ID is called in scope, meaning we're able to access that variable. Now, person ID is in scope here because we are in the same function that person ID was defined. Because it was defined in the same function, person ID is known to be within what's called local scope, meaning it is locally available to us. We can update it and do whatever we want to it. There is also another scope called global scope, where if I make a variable that is outside of these parentheses, that means that they are outside of the scope of a function, that means they're in what's called global scope, meaning that any other function has access to them. So I can make a variable called integer g is what we want to tag our variable name with, g for global, and we'll say num persons. This can maybe be a variable to declare how many persons that we've tracked so far in our system. Generally, we want to actually avoid variables that are in global scope for the following reason. It's very hard to keep track of where in our code we use global scope variables. Let's say, for example, we have one function that adds the number of persons and another function that takes away from the number of persons. If we do this too many times in a certain order and lose track in our code of where this happens, it's very easy for this to run away and possibly cause logic issues in our code. It's more safe to keep variables in local scope. An important thing to be aware of when it comes to variable scope is that variables can have the same name if they are within different scopes. For example, my main function, person ID, can exist in the main function, right? We have a function called main, and person ID exists within this local scope. If I go to update person ID, I'm only going to update this variable here. The other person ID that exists in some other function's local scope will not be updated by this update. Also, we can define additional subscopes in a function by using additional parentheses. For example, if I use these parentheses here, I can create another subscoped copy of person ID, and I can make it have a different value. And whenever I update this person ID, it'll update the variable at the lowest scope, not the one that's up here. Again, these aren't super applicable right now to our project, but it's really important to know when you create variables, where you're able to access variables, and what is generally accepted as safe and not safe when it comes to global scope variables. In a future course that we do multi-threaded programming, you will see why global scope variables create problems, but don't worry about that for right now. So that's generally how scope works. Move on to the next lesson where we talk about the C preprocessor. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about something that I think gets a lot less attention than it should for new programmers. We're talking about the C preprocessor. The preprocessor is all of these things here that start with the pound sign, and I think typically new programmers kind of ignore it and don't really understand how it works until much, much later on in their programming career. But I think learning it early actually allows you to write code that not only looks better, but is easier to debug. You can add cool features to your code that makes it easier to understand what's going on and to control your code at a higher level. So let's talk about first what goes on when our compiler actually converts our human readable source code, all of this stuff, into code that gets ran by the computer. This is called the compilation process, and it happens in 4 steps. But the very first step that actually goes on before anything else happens is the preprocessor gets ran on your code. And what the preprocessor actually does is it takes these directives and copy and pastes whatever is meant to happen in this directive into your code. So for example, the pound include directive literally reaches out to the global standard IO header file and copy and paste that into your code. What that allows us to do is access functions that we didn't write, like printf or scanf or puts, other functions in the standard glibc runtime that we didn't create. That's what pound include does. And then pound define is another cool preprocessor directive that allows us to create variables that act as constants where we can control how our function behaves through these variables at compile time. For example, if we have a structure of the number of people we want to have in our database, we can make a max persons pound define that we can actually access from the compiler at compile time. We can change that when we compile our code and make it do things based on what we need it to do in the compiler. We also have things like pound define debug, where we can later check if this thing is defined, output some code. Otherwise, if this isn't defined, this code won't happen. By having these really cool compile time variables, we can insert things into our code like we are in debug mode, and then use another preprocessor macro like file in line to tell us what line our code is running on. So if we have a crash later on in our code, we know about what line that crash occurred on. So the preprocessor gives us a lot of really high level power to create code that is easy to read, but also is controllable so that we can make major changes to our code with not a lot of changes to the actual lines of code themselves. Like for example, here I can go and I can compile this piece of code, and because I have pound debug enabled, I can run this code and it tells us we're on variables.c line 10. But if I disable the debug flag, that line of code goes away. And I can also from GCC define debug, and I get that piece of code back. So making our code written this way with preprocessor allows us to have a lot of really finite power over our code. So guys, that's it for now. Move on to the next lesson where you'll finally write your own code and compile it and run it on the command line. We'll see you there. Hey guys, what is up? Welcome back to Low Level Academy Zero to Hero C Programming. Today we're talking about the array structure in C. In the previous lesson, we talked about variables, right? And just to recall, a variable is a place where your memory goes. It's pretty straightforward. So if I have int id equals 0, that allocates a little space of memory that is the size of an integer, so 4 bytes. Its name is id, and its value is 0. And an issue kind of comes up if I want to have multiple variables of the same type. I could say int id equals 0. I could say int id1 equals 0. I can say int id2 equals 0. And I can even get really fancy where I can say int id3, id4 equals 0. And I can write that all in the same line. And this is actually all valid C. But the problem is you start to incur this thing called technical debt, which is this idea that updating your code and maintaining your code and kind of making it do what you want to do is a lot more complicated than it has to be. What if you wanted to just have a bunch of integers that represented the same type of data, but there was just a bunch of them? And that's where arrays come into play. So an array is literally just a block of memory that contains a bunch of the same type of variable. That's it. It's no more complicated than that. You do have to make them the same type. You cannot have an array of different types. That's actually what a structure is called, and we'll work on that in a future section. But for now, let's say, for example, we wanted to have an array. An array is created by saying the type and then the name, so I'll call it IDs, plural, because it's going to have multiple things, and then a left and a right bracket. It's called a hard bracket. This denotes an array. Inside that array bracket, we have to denote the number of elements that are in that array. And typically, it's good practice to pound define a variable. We'll call it max IDs, like the maximum number of IDs there are, and we'll put a number in there. We'll say 32. And now I will type the max IDs value inside our array brackets. So this tells the compiler that we want to create an array of 32 elements. The elements are all of int size, so 4 bytes, and its name is ID. Another way we could have made this, and we'll comment this out so we don't get an error for duplicate effort, is that we could have said int IDs without a number inside of them, and we can let the compiler infer how many we want by declaring them at start. So we could say int IDs equals, now we use a curly bracket here, note the difference, we have a hard bracket here and a curly bracket there, and we can say 1, 2, 3. What that will do is that we'll create an array of multiple objects, of multiple ints, by default it'll make room for 3 of them, and its values will be 1, 2, and 3. So you're probably curious now, if we have this array, and I'm going to uncomment this, we can use this one with the better syntax. We'll say that for right now, the default value in our array is 0, 1, 2, and we'll assume the rest get zeroed out. It's a bad assumption, but we'll get to that in the more advanced sections for the course. Now, if we have this array, how do we use it? How do we get stuff in and out of it? Well, to access a value that is in an array, all we have to do is type the name of the array and then the index that we want to get out of the array. So for example, if I wanted to get the 0th element, which is the first element, that's kind of a new thing for some people, indexes are starting at 0. So if I want to get the first element, I actually get the 0th element. And there's actually a pretty cool reason for that. We'll talk about that in a future section. But I say IDs of 0. That will get me the first element in this array, which is going to be the 0 number. We can prove that by doing a call to printf. We haven't talked about function calls yet, but just follow along with me. Do printf %d, which prints out a decimal number, then do /n, and then IDs of 0. This is telling us basically we want to print out a format string. The format string is going to print out a decimal, and what is that decimal? It's the element that is in the IDs array. It is the 0th element, so that'll be the number 0. We'll save that. We'll do gcc taco array.c, and we'll run that, and we get 0. And we can do the exact same thing. Again, we can do IDs of 2, for example. So we're going to get the 0, 1, 2, the second element. It's going to be the number 2, right? Go ahead and compile that again. We'll do array, and we get the number 2. Pretty friggin' easy. How do we assign values after it's been created, for example, right? We say IDs. Is my fat head blocking the video again? No, we're good. We say that IDs of some element. We could say that IDs of 3 is equal to, say, hex 41. We can also do the hex type here. And we can do the exact same thing. We can print out %d/n, IDs of 3. Go ahead and compile this and run it, and we get 65, which is the decimal value of hex 41. So don't get too confused by that. It's just the comparison or the conversion between hex and decimal. So that is how you do arrays at a very basic level. Again, thinking about how arrays will apply to your database project, right? Instead of having a bunch of IDs for people that are separate variables and a bunch of strings for people and stuff, instead of that, we can use the arrays to make our database essentially just an array of people structures, right? We'll get deeper into that as we go into the future sections where we actually create these structures and begin to build out the database. But this is how you use data types that are repeated contiguous memory of the same type. It's called an array, and this is the syntax of how you do basic stuff with arrays. So keep going. In the next lesson, we'll talk about strings and how effectively a string is just a fancy array. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programming, Low Level Academy. Today we're talking about strings, and we just got done talking about arrays, and there's a really good reason why these two lessons are together. Again, an array is just a block of memory where the type of the memory describes how big each element in that array is. So here, for example, we have an integer array whose name is IDs. It is 32 elements in size, and it's defined as 0, 1, 2 are the first 3 elements, and the other ones are undefined at this time. The reason why I want to talk about strings in this lesson is because typically, the first thing that we write in code is hello world, right? We say hello world, and we kind of just print it, and we're good to go. And we don't really know what's going on under the hood here. Strings are denoted by these two quotes here, right? We have two separate quotes that denote that this is a string on the inside. What a string actually is under the hood is just an array of characters. It's really cool because you can make your own custom string like this. We'll say char meister, and we're not going to make a pointer like you see in a lot of other programs. We're going to make an array of characters and say it's equal to HELLO, and I'll close it off. And I want to make sure my fat head isn't blocking the code this time because I already recorded this and I was blocking it and I was like this big. Anyway, so we're going to go ahead and instead of printf that, we're going to printf a %string, and it's going to be meister. Okay, so let's go ahead and print that out. And we're gonna head, and there you go. So we can literally make our own strings like this. Now there's no good reason to do that, right? Obviously you can just make your own string like this. We can say char my other stir equals hello, and this does the same thing, and it's a lot less gross than this. I just wanted to drive home the point that a string in C is literally just an array of characters. Pretty cool. There is one issue with this though. You're probably wondering, how did the computer know to stop printing? How did it know to like just only give me this data and then stop giving me other data? Well, we actually have a small vulnerability here where you have to have a 0 at the end of your string. Strings in C are what is called null terminated or 0 delimited, which essentially means that it's going to print every character that it has. It'll print H, then E, then L, then L, then O, and it'll stop when it gets to a 0. If we didn't have this 0 here, for example, and maybe there was additional data at the end of the 0 that at the end of the O that wasn't a 0, the program would actually continue to print and leak to us information about the program. It literally would just give us data that's on the stack of the program where the memory is and show it to us, even though we're probably not supposed to see a lot of it. It could reveal memory about how the program is protecting itself. It could allow us to hack the program. It's very important to make sure that your strings are null terminated. And you're probably asking, why aren't we doing this here? It's because when you put a string in double quotes like this, as opposed to single quotes and making your own array, the compiler knows by default to null terminate this. It's a thing that it does on its own automatically, so you don't have to worry about it. Now, I know this lesson is called string operations. There are a few operations that we're able to do on strings that behave this exact way. They do the operation until it reaches the null byte. So these functions are things like stir copy that put data into a destination location from a source location. It'll literally just run the copy operation until it encounters a null byte. There are things like stir end copy, which take into a destination a string from a location that is up to n bytes long. And there's a bunch of other string operations we'll talk about later on in the rest of this lesson and the rest of the course. I can't talk about these too much just because these are all pointers and we have not talked about pointers yet. So when we get to pointers, we'll go a lot deeper into the string operations. But I wanted to just drive home the point that if you are having a hard time understanding arrays, if you think about a string as just a block of contiguous memory of the same type, you're literally describing what an array is. So they are basically the same, just this one is an integer array, this one is for characters. So in the next set of lessons, we're going to actually start doing stuff with our data. We'll go into control flow for our program, how to make for loops, how to make while loops, how to check if one value is greater than another, so we can actually start having our program make things happen. So we'll see you guys there. We'll see you in the next lesson. Take care. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgramming on LowLevelAcademy. Today we're talking about, finally, I think what is the fun part of programming for people learning to code is conditional statements. The reason for that is because like so far the code has been kind of boring, right? Like we're like, okay, cool, int I equals 0, and like we make some variables and maybe we like print hello world or whatever. But this doesn't, like, who cares, right? This doesn't do anything. We can't make this code sexy because there's no logic happening. And what are computers meant to do? They're meant to process logic. So today we're talking about conditional statements. What is a conditional statement? Well, let's first have the program declare a temperature variable, and we're just going to have it read from the user that value. Again, don't worry about the syntax for this. You will understand this when we get to pointers, but just copy this out of the area below where I have the code prepped for you. And this is going to read from the user a number that is a temperature. And now I want you to print if the temperature is above 70 degrees, it's hot. If it's below 70 degrees, but above 30 degrees, it's mild. And if it's below 30 degrees, it's cold. Now, the way that we have to do this is through conditional statements. They're called if statements, is the first one. And an if statement is just like it sounds. We have the if statement, we have the condition, and then if the thing that we ask about inside of these parentheses is true, then we run the code in these brackets. So we can start and say if the temperature is greater or equal to 70 degrees. And we're going to say dang, brother, it's hot. And there we go, pretty straightforward. Well, now, like I said, we want to check a second condition. Now, there's two ways we could do this. We could type the if statement here and say if temperature is greater than or equal to 30 degrees, and, this is an and statement, temperature is less than 70 degrees, we can say printf, dang, brother, it's mild, right? Now, there is actually a different way we could do this. This condition is going to get checked. It's going to check if temperature is greater than or equal to 70. It's going to run the check every time. And then whether or not it runs that check, it will also run this check, right? These checks are both going to get ran every time. They are independent of each other. Instead of this, because these are exclusive clauses, right? It cannot be that the temperature is greater than or equal to 70 and also less than 70. So what we're going to do is, instead of saying two separate ifs, we're going to say else if. What this means is we run this if, and then we only check this clause if this one does not fail. If this one passes and we get to this condition running, we don't even care about the rest of the code. The code does not run. We do not even try to do this, right? So essentially, two ifs together are separate. They are exclusive. And then an else if means that this one depends on this one failing. And then finally, we can just say else at the end, right? And we could say that printf, dang, brother, it's cold. Sag, I live in Idaho, right? We're going to return here at the end. This is happening like this, the else statement, because there is no other condition to satisfy other than the temperature being less than 30. You know, obviously it could be like 100 or whatever, but that's handled up here, and it could be in this band, so it's handled in here. So this final case is us handling if it's less than 30, right? So this is a conditional statement where we do some logic, and then this conditional statement depends on this one not passing, and then this one finally depends on if these two have not passed, it just defaults to doing this final third thing, which, based on how we designed our program, will only happen if it's under 30 degrees. Let's go ahead and test this out. Oh yeah, we don't want the new line here. Sorry, delete the new line. Again, all programmers make mistakes. Don't worry about it. Just %d, no new line. And we're also gonna print, you know, we wanna tell the user what to do. What temperature is it? Question mark, and we'll do that. And we'll quit this. And we'll go like that. And then we'll do, what temperature is it? 76. Dang, brother, it's hot. What about 55? Dang, brother, it's mild. And what if it's -1? It's cold. Cool. So those are conditional statements. Essentially, we are using the if statement to make parts of our code run based on certain conditions and other parts of our code run based on other conditions. And then finally, we have this else statement that says if none of those conditions have passed, don't do those, do this instead. Now, as it applies to our database project, when we get into building our menu, right, if the user provides an option to do a thing, you know, if menu option equals add or edit a employee, you know, we'll do a particular function here. Otherwise, if the option menu maybe was to delete an employee, we do a function here. These are the building blocks of coding that we will use in the last module to go through and build our big project. So please take some time, really write some code, understand this, and we'll move on to additional control structures and control flow structures later on in the lessons. We'll see you there. Hey guys, welcome back to your next lesson in Zero to Hero C Programming, Low Level Academy. I've been saying that a lot. It feels good to be saying that because I'm happy you guys are here learning with me. So again, like I said in the pacing section of the course, where I really want you to take time and sit back and absorb this material, the reason I said that is because the material is going to ramp up in quantity a lot as we go through these next couple of lessons. The content gets a lot more dense, and I want to make sure you guys really fundamentally understand this stuff before you go and try to apply it to, you know, building significantly sized projects, especially for people that are new at programming, right? So if you feel like you're comfortable and you're actually getting the material, then good, please keep going. If not, please take a step back, go watch the material again, make sure you really understand it, then keep going. Okay, so in our previous lesson, we went through and I talked to you about how to do conditional statements, right? So we have int ID equals 1. Maybe this is a user input generated thing. And we say if ID is less than 0, or if it's greater than 0, we'll do something fun, do something neat, right? This is just us checking the input and seeing if it meets one of our logic constraints. And if it does, we do a thing. Awesome, pretty straightforward. So what if we wanted to do multiple things over and over and over again, right? We could use the array case for an example to kind of drive home why this is so hard. Int IDs of max IDs equals, we'll put 0 here. What this does actually just initializes our entire array to be 0. And we'll do, again, pound define max IDs to be 32. Now, what if I prompted you? What if I told you that our requirement was to have every IDs of, so IDs of 0, equal that value, right? If I wanted to have IDs of 1 equal 1, right? Again, this is arbitrary, but it drives home the point that we're going to start finding ourselves repeating ourselves very, very often. This is going to get very annoying and complicated to deal with. So what we can do instead of doing this really gross looking horribleness that I never want to see again is do what is called a loop. So a loop is literally what it sounds like. Picture a circle, right? It just goes around in a circle, it keeps going. A loop, it just means do the same thing over and over until some condition is met. That's all a loop is. And in C, we actually have two, technically three ways of doing this. We have for loops, we have while loops, and we have do while loops, which is like, it's like a while loop, but it has like a special condition. We'll talk about that right now. So a for loop is a special kind of loop where the syntax is like this. Typically, we create what is called an iterator. The iterator is denoted by the letter I, right? Typically, if you say, you see for I equals, the reason you use the letter I is because I stands for iterator, because we are iterating over something. Now, what the for loop is going to do is it's going to have inside these parentheses, it's going to have three clauses. We are going to first initialize our iterator. And you're probably saying, why did we do that? We just did that up here. Well, it's bad practice to not initialize your variables, and it's not good practice. It's bad practice to initialize your iterator. So we're going to do it twice because that's the right thing to do. And then we're going to have inside of the second part here, the second semicolon buffer area, we're going to have what is called our truth clause. So the truth clause is the thing that is going to be evaluated to see if we have to run again. So if we're iterating over our entire array, we want to use I to do what's called index into the array. And we only want to do that while I is less than max IDs. Because if it gets bigger than max IDs, we're indexing out of that array, and then we're doing illegal things in C. And then finally, we have the last part of this, which is the take action clause, or the thing we do after every loop. And what we're going to do here is do I++. This is going to increment our iterator by 1. So again, the syntax is initialize your iterator. How often does this run? What has to be true for this to run? And the truth is that I is less than max IDs. And that's obviously true at the beginning, and it will continue to increment I every time until this is no longer true. And then we put the thing we want to have happen every loop, right? Because this is going to happen max IDs numbers of times. So what we're going to do is we're going to say that IDs indexed by I is equal to I. Okay, that's going to say IDs of 0 equals 0 the first time. And it's going to iterate, it's going to check, is I less than 32? Yes. So now I equals 1. IDs of 1 is equal to 1, and so on and so forth. And just to prove this, we're going to print two numbers. We're going to have %d colon %d. And those two numbers are going to be I and IDs of I, right? We're just going to print that out every time. And don't forget your new line character here, because otherwise you get a bunch of crap that doesn't hit enter and it looks like garbage. Yes, we'll write this. There we go. So this is exactly what we thought it would do. It would do for 0 through up until 32, right? Which were less than 32, so it's actually 31. and then it set IDs of that number to that number. Let's try it again, but just to prove that it's different, let's set it equal to IDs of I equals I times I. So now we're doing some fancy like squaring, right? Okay, so 1, 2, 9, 16, right? So we're getting all the squares of these numbers. Pretty cool, right? So that's the for loop. Very straightforward. Again, initialize the iterator, the truth condition to run the for loop, and what do we do at the end of every for loop? Now the while loop is actually even simpler than the for loop. So we're going to reuse our I variable here. So I'm going to say that I equals 0 again. Now the while loop has only one condition, right? Inside this bracket, inside these parentheses is a truth statement. And all we have to do is write a thing to be true for the while loop to execute. So we'll say while I is less than max IDs. Now it is simpler than a for loop, but we are actually the ones on the hook to increment our iterator now. So we have to, at the end of every while loop, do I++. And we'll do the same thing we did before. We'll do IDs of I equals I times I. And this will have the same exact effect as this line here. And I'm going to go ahead and compile this and let you guys see it running twice. All right, so we have, ooh, did I introduce a bug? Oh yeah, dude, this is why C is so crazy. Again, we're not going to go into the details of this, but basically because I incremented my iterator before I printed, I was able to index outside of my array and reveal a number that was out of the bounds of the array. So this is actually a bug, and you have to make sure you put your iterator at the very end of your for loop. That's a fun little Easter egg for you guys. And I'm not going to cut that out. That's a cool learning experience. But I will show that the for loop is doing one thing. You know, it's doing the same thing. It's just this is a different syntax doing the exact same functionality. And then finally, we have the do while loop. So the do while loop is basically a while loop, only it will always run one time. So we can run the exact same logic here. We'll say that I equals 0 to reset our iterator. I'm going to steal all this. I'm going to put it in here. I'm going to learn to use Vim one of these days. Okay. And we're going to say while I is less than max IDs. All right. It's going to do the exact same thing. We should see this happening 3 times. Oh, sorry. It's do thing while. I apologize. I missed that on the syntax there. Cool, so we run this, and we should say it happening 3 times. 2 and 3, there you go. Exact same functionality, just through 3 different ways of doing it. Yeah, so this is a while loop where while will check this condition, and if this condition is not true the first time, it will not run, period. Whereas this will run one time, always, and then check the condition. There are certain instances where that matters, and we'll get into that when we actually build our project. You know, there may be a case where you want to run an area of logic and then check the condition after your logic runs. And if it's continuing to maintain a certain state, do that again. That's where do while is good. But yeah, so these are our loops. This is how loops work in C. These are the only loops that exist. I hope you take this away and pull a little bit out of this. When you are iterating over a large structure and you need to do some kind of repetitive logic over and over again, loops are super useful, and I'm sure you can see why. So that's it for right now. We're going to move on to our next lesson, which is functions. Functions are super, super important in C. It's going to really, really allow you to break your code into multiple parts that make sense, and we'll see you guys there talking about how to make our code a lot less ugly and a lot less long like this. So we'll see you in the next one. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgramming, LowLevelAcademy. Today, we're talking about functions, right? What are functions? What is the syntax of functions? What is good practice for functions? All that stuff, we're talking about it today. Let's dive into it right now. So like I said on the previous lessons, right? Your main function is basically just the block of code that will run every time your program starts. The compiler expects main to exist. Now, inside of these little curly brackets, there's something I've kind of been ignoring, but it's what's called the function parameters, right? The arguments that are given to your function to make it do stuff. We're not going to talk about the arguments to main right now, just because, they're a little complicated. They have to do with command line arguments, but technically there are arguments that go to main that looks like this. If that scares you, that's okay. It scares me too. Don't worry about it. But let's talk about how we can use functions to make our code look a little cleaner, right? So how do we write our own function? What is the syntax of a function? The syntax of a function is very, very simple. So typically what we do is we say something like the return type of the function, then the name of the function, then the list of arguments, and then we define the function, right? And we go like that. So this is how every function in C is defined. And that's exactly how the main function is defined, right? We have a main function, the name is main. It returns an integer, which actually is the value that tells the computer if our program failed or not, right? And then we give the argument parameter list, the list of things that the function needs to behave, right? Our input from the user. Now you're probably asking, what does return mean, right? What does this return type have to do with anything? Well, let's say, for example, I wanted you to make a function that added two numbers. The result of that add function would come out of the function through the return value. So what that means is that it would give back, as a result of the function, a number, and that number would be an integer type. So let's say int add. And then the values that I want you to add together are going to be the arguments to that function. So that means that we want to give the add function two inputs. So it'll be integer x and integer y. And now we have to define what that function does. Add will create another variable called z, and z is going to contain x plus y, and then we're going to return z. What this means is that whoever ends up calling the add function will be presented with the result of the addition. It'll be presented with z. And again, it's important that we make sure that these types align. Int z is a type int. We're returning z. The return type is int. Everything is good. We're good to go. So let's go ahead and say that we have int other int is equal to add 1 and 2. This is how we call the function, right? We say the name of the function, then we put these little parentheses around it, and inside those parentheses, we put the numbers that we want to pass to the function. The function will then get ran right here. It'll jump up here to our function. It'll run the functionality and then return that value. And now we can do print %d, and then we'll do other int. Right, we're just going to print out that value. And just like the add function, when we've been doing printf this whole time, kind of something I've been glossing over, we are calling the function printf, which exists in a different library. And the arguments to printf are this string that tells it what to print, and then the list of arguments like other int, the thing I want it to print, right? And then finally, we're going to be good little programmers and return 0 from main. Let's go ahead and compile that and see what we get. So gcc taco functions.c, and we should get 3. Very nice. Easy peasy. Now that's how you use a function, but why do we use a function? I've talked a lot about this in my videos, but the high level idea is that it's good to be lazy as a programmer. And what do I mean by that? This add is kind of a bad example, right? Because this line is a single line of code. It does not need to be its own function. But let's say that we made another function called initialize employee, or let's make this initialize employee structure. And we'll say that the argument to this is going to be an employee pointer. And again, we haven't talked about pointers yet, but just trust me that this could be a function, right? Inside this function, we would do what the name of the function says. We're going to initialize a structure to contain employee data, right? If we are going to initialize multiple employee structures, if we're going to run that code multiple times, we are incentivized to write code one time. Do it once. We don't want to do things multiple times. Dry, D-R-Y, don't repeat yourself. By writing a function that does something, we effectively put all the logic to perform a certain task in one place, so that instead of writing that logic over and over and over again and like being bored of just writing the same code over again, we can write it one time and use it over and over again. So as we begin to develop the logic behind our employee database, a lot of that's going to be dependent on creating functions that perform singular, simple tasks. So we'll have one function that initializes the employee structure. Maybe I steal this definition and I make one that says destroy the employee structure, right? We have a single employee structure. Maybe this is the one that sets it up and mallocs it from the heap, and then we return it. And maybe this was the one that, clears all the fields and removes it from our file, right? By making a function perform one single task, a single task that you can describe in a sentence, right? Initialize structure, destroy structure. It makes the code very easy to organize and design your system in a way that you can write code cleanly. So that's it for now. That's kind of at a high level how functions work in C. I want you guys really to take this in and start to visualize based on how you saw loops working, based on how you see these functions coming together, based on generally how you do user input. How would you begin to organize a program that you need to create a bunch of data that stores employee information? This will become a lot more clear when we get to the structure part of the lesson, because that allows us to make structures that have different data types. Right now, we're kind of stuck with arrays, and arrays only have one kind of data. You can have an array of integers, you can have an array of characters, but you can't combine characters and integers in the same structure. Later on, when we get to structures, the thing that allows us to put multiple of those together, it'll start to make a lot more sense how this whole thing is going to come together and make a really, really cool project for you to play with the C language. So let's move on to the next section where we get into data types and eventually structures and start tying this all together. Let's do it. Hey guys, what's up? Welcome back to your next lesson in Zero to Hero C Programmer on LowLevelAcademy. Today we're talking about a really, really important concept in C that will begin to actually allow you to create the scaffolding of your employee database project. So previously, we had talked about these things called arrays, right? So if we had multiple IDs for multiple employees, for example, that we wanted to logically combine them, we could do it like this, but this gets very complicated and kind of annoying to manage. We have to like manually set these each by name, and then later on in the code, we have to say like if ID2 equals some value, and then do some logic based on that. And this is very hard to grow as a code base. You can't do anything with this without having to manually add lines of code per new ID. It's disgusting. So what you do instead, that we talked about in one of our previous lessons, is an array. So we can say int my IDs, plural, and using the square brackets, we can declare up to n, so n being 32. And again, we said max IDs, we want to create a constant, right? Reminding you of all this. Pound define max IDs is a 32 value. So we can create an array, and we can join all of those IDs together. Now, this begins to make your code a little simpler, but we don't really want to logically combine all of the IDs in our database. We want to logically combine all of the employees in our database. And the problem is, what if the employees have multiple kinds of data? What if they have a float, like a decimal income value? And what if they have maybe a name buffer where we store their first and last names? 64 characters allowed for that. A lot of issues come up where in an array, we have to combine only the same data types, but I want to join multiple data types together. This is where a structure comes in. And this is where we're going to start to define some structures that we're going to use in our project. So to create a structure, and again, a structure is a block of memory where multiple data types of different or the same types are combined together in a logical block, right? So for example, I can make a struct employee T, and we use the underscore T to denote that it's a type, and we can define that by saying employee T, and then we do curly braces, and now we can start to put in the fields of that employee T. So I can say int ID, I can allocate, let's say, first name, and I'll give him 64 characters for their first name. I can give last name 64 characters, and we can do float income, and I can say bool is manager, right? We can do all this stuff. So what we've done now is, instead of having an array of all these different types together that really, like, it's kind of clunky, we can logically combine all of this information to represent a single employee. So how do we use that? Well, let's create a struct employee here in our code and kind of go through how we'd want to put this code together. So let's say we have struct employee T, call him Fred. And we could say that Fred.income equals, we'll give him, he makes $100 an hour. This guy's rolling in the dough. And also Fred.isManager is true because he's our manager. By writing our code this way using structures, we can combine this information in a way that's actually logical as a human would expect it. A human would not expect an array of IDs, an array of incomes, an array of managers. It would just expect the information to be aligned against a single person so that we can manage that single person. So combining this idea with arrays like previously, though, we can start to do really, really interesting stuff. And this is where the main part of the database is going to start to come into play. What if I wanted to have an array of employees, right? I mean, I can do an array of ints, right? I can do int my IDs. Can I not just do struct employee T employees array? And we'll say we allocate 10 employees. We can actually do exactly that. And this is almost the entirety of the employee database. Obviously, we need to write code to add and edit and take away, do it safely. But at this point, you've created a structure in memory that has room for multiple employees. And if you're able to read and write this out of a file, you've created almost the basis of storing this information about the employees, which is pretty interesting. So how do we use this? Well, let's use our for loop from the previous lessons. We'll do for I equals 0, I less than 0, or let's do I less than 10, I plus plus. Actually, no, this is bad code. What we'll do is we'll make a pound define max employees, make it like 1,000, right? Let's show that our code is saving us time, and we'll do max employees. And we're going to use that number here, max employees. And then we'll go through and we'll just initialize every employee. So it's employees of I dot income equals 0, right? Employees of I dot is manager equals false. There's lowercase f in C, right? And so we are able to now do things programmatically using the employee structure and using loops where we are able to have really, really logical control over this data using the power that C gives us. And again, talking about functions before, we would probably create this as a function like, initialize employee database, something like that. We'll get into that in module 12 when we actually begin to logically design this program. But I want you to understand how much power the struct keyword gives you in C, because it allows you to organize your data in a way that you would logically expect it. And then you can use the control flow statements in C to allow you to edit it in a way that makes sense to you. So go through, play with this, do things like print, let's do %d employees of 10, right? So get the 10th or the 11th employee. And print there, let's do income, right? And this is actually going to be a float. It's not a %d. Let's go ahead and run that real quick. GC taco struct.c. Oh, no, it's standard bool. Yeah, sorry. So to use bools, you have to use standard bool. But if we do struct here, we'll show that the income of the 11th employee, because we haven't initialized it yet, is $0 an hour. Very sad for that guy. So anyway, get into your code here, start messing around, start writing different parts of your employee structure now, start adding code where you're able to, set these values, just play around with the structure, make sure you're comfortable with it, and then understand that you can create arrays of structures to really begin to scaffold out what that database looks like. So keep going. We'll see you in the next lesson where we talk about unions, which isn't super relevant to this project here, but it's important to know what a union does. So talk about that and see you there. Bye-bye. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming on Low Level Academy. Today, we're talking about unions. Now, unions are not super relevant to the course project that you're going to be writing at the end of the course in module 12, but I think it is important to talk about because it's one of those things that people probably see in code as they're maybe reading other code bases and don't really know what a union does. So in a struct, for example, or a previous project or a previous lesson, a struct will allocate enough memory to contain all these elements, right? I want to have enough room for an ID, and then 64 bytes for a first name buffer, and then 64 bytes for a character buffer, float income, etc., right? So it's going to allocate all the memory for all of these types. Now, the union type is a little weird. It's a little different. So a union will create enough room for the biggest element. You're probably kind of curious, like what purpose does that serve? So let's do my union U. Just call it a union. It'll create enough room for the biggest element. So for example, if I have int x and I have char c, the union will only be int x wide, which is 4 bytes on the system that I'm using right now. The reason for the union type and why it kind of exists is if, for example, you were doing embedded stuff and you wanted to have access to all 4 bytes within the 4-byte int type and didn't want to have to do the manual math every time, what you could do is by looking at the value c, you would get access to the first byte of the 4-byte character x. I know it's not like super relevant for this project here, but just understand that a union is a type that only creates enough room for the biggest element, and you're allowed to access all the sub elements. And I can do like short s, for example, right? But let's kind of show you guys how this works. So I'll make a union, my union u, we'll just call it u. We'll say that u.x equals 41, 42, 43, 4. And what I'll do is I'll print all the different parts of it. So I can do %hx, which gives you half. And I'll give you %hhx, which gives you half of half, so a quarter. And then I'll print that and I'll give it, we'll show you the short u.s and we'll do u.c. And this will show you basically that when I'm using the union, I set the larger value. And by using u.s and u.c, I'm accessing internally the smaller parts of this bigger x. I know, super weird, super complicated. Don't worry about it for this project too much, but it's just good to be aware this is that this exists. Do gcc taco union, union.c, we'll run union. Yeah, so again, by showing you, we made the value hex 41, 42, 43, 44. By using union.s and union.c, we got access to the internal short and the internal character of that larger int x. So keep going, don't worry about this too much, just understand that a union exists and that if you're doing more complicated memory management related embedded programming, for example, you'll need to know what a union is. So keep going, we're gonna talk about next special struct modifiers and how we're gonna use those in our project to pack our structures super tight so that we know exactly where the memory is. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about some special struct modifiers that we can add to our structures to make them a little cleaner, but more importantly, to make our code interoperable between different systems, right? So when we have a structure, we talked about this before in our last 2 lessons, we're creating enough memory for all of these types. Now, what that kind of implies in your head is that, oh, okay, the size of the structure is equal to the sum of all of the sizes of the parts, right? Well, that's not actually true. Depending on the system that your code gets compiled and ran on, it may add additional optimizations under the hood that add padding characters in between these fields that you're not aware of that are there. And the problem with this is that if you have 2 different copies of this code that gets compiled on 2 different systems, but you expect them to talk to each other externally, the issue is that if they're optimized for different reasons, the structure begins to look a little different, and you can't actually expect the offset to ID on one system to be the offset to ID on another system, right? So to prevent this issue, what we can do is we can add special struct modifiers onto our code to make sure that there's no additional optimizations put in between the different fields, right? To do that, we'll do attribute underscore packed, and it's actually gonna be 2 of these, like this, and then we'll go from there, and we'll do gcc taco struct and struct. And if you ever want to test this, what you can do is actually check the size of a structure by typing the size of macros. We'll do size of employee is %d, and we'll say size of employee t. This will get us the size in bytes of that structure. So let's do it the first time without packing the attribute to kind of show you what it might blow up to. Do this, we'll do GCC, Oh, I'm sorry, you have to do struct employee t. Size of struct employee t. Struct, so it's 140 bytes, which makes sense. 64 plus 64 plus a few others. And we'll do struct vim struct. Now we'll do attribute packed. We'll see if I actually saved any space or if I'm just made of nonsense. You see struct 140. Okay, well in this case it doesn't matter, but this will actually save you a lot of heartache in the future if you're sending this data across different systems or you want to store it into a binary structure on the disk. So with that being said, take this time, go write some code, go use some structures, and get your mind wrapped around how you can use structures in your employee database in the final module, and we'll use that there. So we'll see you in the next lesson. I'm pretty sure about pointers, and we'll see you. Let's go do it. Goodbye. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programmer. Today we are going to be doing a lot of stuff. We're going to be learning not only about pointers, but we're going to be taking previous lessons information like structures and functions and putting them all together and showing you how these concepts really do stack on top of each other to allow you to write really powerful code. So again, like I said in the pacing lesson, please take your time. Please spend time to absorb this information and really make sure you get it before you start stacking ideas, because if you don't and you rush, you may find yourself really starting to slip and not have a strong foundation. But if you're comfortable and you're ready to get into it, let's get into it. So I find that pointers are an idea in programming and specifically in low-level languages like C that really trip up new students. So I want to kind of talk about what a pointer is, why we use them, and how we use them all in this lesson. So a pointer is literally just a value that happens to be an address. That is it. And what do I say when I say address? What do I mean? So let's say, for example, I make a value called int x, and we'll say that int x equals 3. When I type this line of code, what the compiler does is it makes room on what's called the stack. It's basically just a memory location in the program that you put things that you're using at runtime, right? When I make room for x, the place that I make room for it, or the place that I put it, is the address of x. It's the place that that x lives. So if I were to make a pointer to x, all the pointer is going to be is a value that equals the address of x. So I said that out in English, right? Now let's make that happen in code. So let's say I have an int pointer, that's what the star means, in the declaration side of the expression. So on the left we have the declaration and on the right we have the assignment. On the left, when I say int something, it's an int pointer, and it's going to be px. And this doesn't mean anything. I could literally name this potato, right? But I want to name it px because I want to show to you that it's a pointer to the x value. And then I'm going to assign it. Now, what do I assign a pointer type that I want to point to x? Well, I assign it the address of x, right? So this ampersand means the address of, and then I say the thing. So this whole line in English means create an integer pointer whose name is px, and it set its value to the address of x. That is it. That is all a pointer assignment is. Okay, so when we're talking about pointer assignment, that is the syntax. The star here means a pointer type. But when I'm going to go forward and use the pointer, I have to do a little bit different of the syntax. So let's say I wanted to use int px to get the value of x, right? If I want to use px to get x, I say the thing pointed to, that's what this means. It means to dereference, to turn a reference into a value. Dereference px, right? This literally says get the value pointed to by px. And if you're curious about what px itself equals, what did I say before? Px is literally just a value that happens to be an address. So let's print out the pointer value of px. And let's print out the value pointed to by x. Let's show you what that looks like real quick. Again, so let's look back at our code, right? Vim pointers.c. Right here, I'm getting the value pointed to by px, which is 3, right? And then let's say also I wanted to get the value of px itself. I wanted to show you that it's a pointer. Well, look at that. It's literally just a large value that is an address. Awesome. Now, a lot of people, whenever I show this example, the immediate question is, why are we even using pointers, right? Like in this case, why did you have to dereference px? Why could you not have just used x? And that's actually a really, really good question. In this case, the integer is a bad example because not only are they in the same scope, right? They are like the same size. There's no reason to pass around int pointers in this case, right? But we talked about in our previous lessons a structure. And again, this isn't the exact structure for the project, but I want to show you what we're talking about here. So we have employee t, the structure, and let's say it has an int ID, and it has an int income, and it has a bool or bool staff, right? Is it a staff member or not? And we'll also have to include a standard bool for this. Cool, so we have that. And we're gonna create an array. And we're gonna create one employee t. So we'll say struct employee t, I'll call him Ralph, right? Now, in the previous lesson, what we did is we said, okay, cool. So we're going to initialize Ralph. We'll say Ralph.id equals 1, and we'll say Ralph.income equals 0. Like we're basically setting the default value for Ralph. Well, in our functions lesson, what we talked about is if we're doing the same kind of operation logically on a thing, we want to make a function to do that thing. And we even gave the example, right? We said void initialize employee. Okay, well, if the employee is declared in this variable scope, initialize employee can't access it. So how do we make this work? This is where pointers come in. So what we're going to do here is we're going to create a variable or a function called initialize employee. It's going to take a struct employee t, we'll call it e, as input, and it's a struct employee t pointer, right? It's not the structure itself, it's the address of the employee. And all this function is going to do is initialize the employee. So we're going to say e of id equals 0. We're going to say e of income equals 0. And we're going to say e of staff equals false, right? And then we're going to return nothing because it's a void function. Void function is returned, it is return no value. And so how do we call initialize employee on Ralph? Well, this takes a struct employee t pointer. How do we get a pointer from Ralph? We just say the address of Ralph, right? So this is where he lives. This is his memory location on the stack. And then we say this is the pointer. We pass him in, we set him, and we go from there. And let's just prove that this works by printfing Ralph.income at the end of this code, right? So let's check that out. There we go. His income is 0. Very cool. So this is pointers at a high level. When you have variables that exist that are out of scope, but you want to use them in other functions that logically perform a single task, like initializing an employee or destroying an employee or something like that, you use pointers to pass around the where they live in that scope, and then have that other function now have access to that variable and do a thing on it. So we can use this kind of logical structure here to add new functions like update employee, set employee ID, update income, things like that we'll use later on in the project in the final module when we finally build the whole thing out to really make our code logical and debt-free. Let's move on to the next lesson where we talk about dynamic memory allocation, what that looks like in C, and how it can kind of hurt you and how we can fix it. So let's see you guys there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about dynamic memory allocation, what that means, how you can use it incorrectly, and how to use it correctly. So in our previous lesson, we talked a little bit about how we use structures and pointers together to create code that performs logical functions with data that may be out of scope, right? So for example, we created this employees array here, and I passed the address of the first employee to this function to initialize it, and previously we printed that data out. Now there's an issue with this code from a performance and optimization standpoint, where every time we run this code, despite the amount of employee space that we need, we are always allocating 1,000 employee structures on the stack. Now, we don't want to do that for two reasons. One, it limits us to the amount of employees that we can allocate. We can only ever allocate 1,000. But also B, we're kind of wasting memory here, where every time we run this program, we're blowing up the stack, and it's kind of just a waste of memory, right? So what we can do instead is we can use a memory allocator, and glibc, the libc that you use by default in GCC, has a memory allocator, and you use it in the following way. So instead of employees being an array here, we're going to now treat employees as a pointer, right? And when you do a pointer type, it may point to one element, but you actually can use this pointer to point to an infinite number of elements further out from the base element, right? So now instead of employees being an array, employees is now a pointer, and we're going to set it equal to malloc, right? So malloc is the memory allocator. We're asking libc to return to us a pointer to some amount of memory. And how much memory do we want? We want the size of struct employee t, right? That is 140 bytes, as we saw before. So we're going to ask how big a structure employee t is, times the number of employees that we want. So we could use our max employee structure here, or the max employees value, and get 1,000 back. But what's cool about using malloc is now, instead of using some gigantic constant, we can actually use a runtime value, like I say, int n equals 4, for example. We can use int n equals 4. We can use n to only allocate the amount of employees that we need. Now, it's good practice to make sure that you check that your pointer did not get null returned, because sometimes the memory allocator can fail, and if it returns null, well, then we don't want to use that memory because we can't dereference a null pointer, right? So we can say like printf the allocator failed, allocator failed, and then we return -1, which is the bad error code, right? This is us telling us that the code failed. And then otherwise we do the exact same thing. We initialize the employee, we use the ampersand to get the address of the employee, and we go from there. And then now, once our code is over, we need to give the memory back to the allocator, right? So when you're using code that uses dynamic memory allocation, it's really, really important to avoid what is called a memory leak, where effectively the memory in your code does not get given back to the operating system. And over time, you can actually allocate all the virtual memory allowed for your process, and the kernel will end up killing your process, and it's bad voodoo, right? So what we want to do is, once we're done using this memory, we write free employees, and this will give the employees value back to the allocator. Now, what we want to also do is make sure that we set employees equal to null, right? Because if we have this pointer and it's freed, given back to the allocator, we don't want to enable ourselves to use it, right? That's what's called a use after free. It's a huge set of bugs that create memory corruption vulnerabilities in code. So by not only freeing it and giving it back to the allocator, by effectively deleting the pointer, we remove ourselves the power of being able to accidentally use it in the future, because if we tried to access this, it would crash the program. So let's go ahead and just show you this working real quick. We're going to printf, we'll do %d, I'll do employees of zero.income. We'll do that, and we'll do a little GCC. We're gonna get a bunch of warnings here because I didn't include standard lib. Let's actually go ahead and include standard lib. So as you're using new functions, by the way, in C, what you want to do is do man that function, like man malloc, and make sure you're including the header file that comes with that function, right? The C compiler knows what you're talking about and will do it for you most of the time, but it's good practice to do it yourself, so your code behaves correctly. Good, so we have that, and now we have 0 dynamically allocated, not statically allocated. That's dynamic memory allocation at a high level. Effectively, what we're able to do is, instead of depending on compile time values or values that we know in our code, we can read data off the disk. Like maybe the database header says that, we have n number of employees, we have 4 employees. So this value came from the database header, right? And now, instead of allocating 1,000, right, we can allocate a runtime value, n, and then use that later on in our code. So that's it for now. Next lesson, we're talking about static memory allocation, which is another kind of memory allocation that happens in the program in the data section. But we'll talk about that in the next video. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about static memory allocation. And in particular, I'm talking about the use of the static keyword and kind of what it does, how it works, and where it makes sense to use it. So let's say, for example, we wanted to track in our employee database the amount of employees that had been initialized so far. We could do this kind of in two ways. But the first way is by making a global variable, right? We could say int n employees equals 0. And we'll say this has actually a g in front of it to show that it's a global variable. So we'll say g num employees. We'll do some like camel case stuff here. Now, global variables are kind of a no-no in programming for a few reasons. The main reason being it's hard to track exactly where this piece of data is accessed and control who has control over it at any given time. And especially later on in our code, when we do multi-threaded code, it gets really difficult to make sure that this is accessed in a way that's sane, that there's no data races, etc. So what we can do instead of using a global variable is do what is called a static variable. So let's say in our initialize employee function here, I want to use the static keyword. What the static keyword will actually do is it initializes this variable in global scope, but we are the only ones that have access to it. What that means is that every time the function gets called, this variable does not change its value, right? So to use static variables, what we'll do num employees, we'll do static int num employees equals 0. The first time this code gets ran, it'll be set to 0, and that'll be in a global scope, meaning it'll only get set to that value one time. And then when we run future lines of code after that initialization line, we can do num employees plus plus. It means incremented by 1. This will increment the number of employees variable to 1 plus the previous value, even though it gets set to 0 here. What actually is happening is this variable lives in what's called the data section of the elf. So it's not being put on the stack, it's being put in a location that does not get destroyed when the function returns, and then updating that variable for us. What this does is it actually gives us a practice called data hiding, where we could have made this a global variable, but by putting it in here, other functions can't access the num employees variable. We can't, like, no one else can touch this but us. So it's just a really good way of hiding data so that there's no race conditions. What we actually could do is we could now make initialize employee return an int, and it's going to return int num employees, right? We also could make the ID equal num employees. So now every time we initialize an employee in the database, the ID gets set to the current index. So maybe it's 0 the first time, then it's 1 the next time. And then after that, we return the ID that we got. So let's go ahead and turn this into a loop and say for int I equals 0, I less than n, I plus plus, right? And then what we'll do is we'll initialize employees of I, and then we're gonna printf new employee, ID is %d, and then we're gonna print, we'll do an int in here, call it int ID, we'll print their ID, right? Go from there, we'll delete all this, and we have to make sure we still free the employee thing because that came from the malloc, came from the heap, and then we set n equal to 4. So let's go ahead and see if we get 4 employees, each with a different unique ID. New employee, ID is 1, ID is 2, ID is 3, ID is 4. So static variables are a really cool way of having global-ish data, but keeping it so that the scope of the variable is local to that function, so only you can update it, and then you can use that to return data or add it to logic of your function or whatever. So that's it for right now. Let's go on to the next lesson where we talk about the heap is kind of a scary place. How do we check to see if we're using the heap properly? And if we aren't, how do we check for memory leaks? We'll see you guys there. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgramming. In this lesson, we're talking about these things called pointers to pointers or double pointers. Typically, this is a concept that trips a lot of people up when they're learning to code in C because it's a weird concept. Pointers on their own are kind of difficult. You then introduce this additional layer of complexity where you have a second layer of pointers, and people tend to not understand why they exist or how they work. So I want to go into that in this lesson because this will actually matter a lot for the end of course project. So let's dive into it right now. So we've talked about pointers very recently, right? A pointer is just a variable that contains an address of another variable, right? And in this example here, we have the integer I. Int I is just a space on the stack that contains the value I, and I is just some number, right? Now, what we can do is we can take the pointer to I by creating an integer pointer. So we say that int star pi is equal to the address of I. When we create a variable declaration, the left side of an equal sign, this type with the int star means it is a pointer, right? We've talked about this before, pretty straightforward. The additional layer of complexity comes into place where we have this to star thing, right? So again, talking about pointers left to right, the int star star named ppi is equal to the address of pi. So all we've done here is we've created a variable that is a pointer to a pointer whose name is ppi, and its value is equal to the address of pi. And that makes sense, right? Because it is a pointer, it is the address of a type which is a pointer. Now the question that really bothers people, and again, like this from a conceptual standpoint is very simple, right? But how, like, why does this matter? Why do we do this? Well, take, for example, the case where we are getting a pointer back from some kind of dynamic memory, right? Like we have malloc. Malloc's going to give us a pointer to data that lives in the heap. We're going to use that in the employee database to store our employees. But the thing is, if we have this pointer come back from malloc, how do we give it back to the program? If this pointer to the data lives in one function, but I want to use it in a different function, how do we do that? Or even more particularly, if we reallocate the pointer, if we change the value of data, how do we update it? The double pointer is going to give us the power to put the data pointer somewhere else. We're able to use a pointer to update the pointer with a new address. So for example here, we have this function called foo, and inside of foo, we call malloc. Malloc returns a pointer, and we want to extract that pointer outside of the foo function so that we can use it. Now you might be thinking, okay, isn't that the whole point of a return value? And that is one way we could pull the pointer out, but we also in functions want to return some kind of status, right? So instead of returning the pointer from the function, we're going to return this type we made up called a status t that just says if we did or did not fail in the function. That's not super important, but what is important is there is a parameter here that is a pointer. It is the data out. And the reason that it's a pointer is it is the address of an address. And what we're able to do is instead of calling malloc, getting the variable out, and then returning it by the return value, which we can't do because this is a status t here, we're able to overwrite the value at data out by saying star data out equals that value. We're using this double pointer as a way to extract data from the function and set the value at data out to this new malloc location. And this will be used in the employee database when you have to expand or contract the size of your employees based on if you add or delete one. You will need to reallocate a heap buffer, and you're going to have to extract that pointer via a double pointer. I'm going to go write a snippet of example code real quick. So to kind of show how our double pointers work, I made this cute little example, right? So here on line 24, we have a pointer to an integer that comes from the heap via malloc, and malloc allocates 64 bytes. And then we call our function foo on the address of this pointer. That turns this label here into a pointer. And what foo will do is foo will try to reallocate the pointer to a particular size. And we can go through and read foo here. So foo returns a status t, which is a type that I made up that just says good or bad. And we're doing this so that we can tell the programmer via the return of foo if something inside the function went wrong or went right. It's just another way of designing your functions. So the foo signature takes an int pointer, which is an address of an address, and then the length. We have a temporary pointer, and we try to reallocate this data pointer, and reallocate just makes a malloc buffer bigger or smaller. We say reallocate the thing pointed to by data, because that points to our pointer, to a certain size. If temp fails, we are going to set that pointer equal to null, because now it failed to reallocate, and then we're going to return status bad. Otherwise, if it passes, if all of the stuff goes well, what we're going to do is we're going to say the thing pointed to by data is equal to this new temp variable. So we're literally overwriting this address with this new address, because reallocate is returning a new pointer from the heap. And if this fails, we say, uh-oh, otherwise we just go on and use the rest of our program here. So in this example, all we're doing is we are taking
a address to a pointer, which is now a pointer, and we're using that to overwrite it with a new pointer from a function like malloc, for example. And that's it. So if we run this, we should see that the program A doesn't crash, but also B doesn't say uh-oh. So let's do that. We'll do gcc taco double.c, and we'll run double, and we're good to go. So that's it, guys. That is pointers. I hope that kind of clarifies it. Please take this time, go write some code yourself, feel how this works, and then go to the exercise in the next lesson, and we'll see you in the next one. Take care.
Hey guys, what is up? Welcome back to your next lesson in Zero2HeroC programming. Today we're talking about how to detect and fix memory leaks in your code. So like I said previously in the past couple lessons, it's better to use the heap in some instances where you want to have dynamic memory allocation, where the amount of memory you want to access is a function of some variable that you have at runtime, right? The issue with malloc is that it's an allocator. You're borrowing memory from the system. You need to give that memory back to the system. Otherwise, you have what's called a memory leak, where effectively over time, the amount of memory your program uses grows over and over and over again. Eventually, you may consume the entire system's memory, your program can crash, etc. It's just bad practice. You always want to give the memory back. So in this code, I'm not going to say exactly where, but we have a memory leak. We have a place where we do not give the memory back to the system, and I want to figure out where that happens so I can fix it, right? Now there's two ways we could do that. We could do a manual source code audit and look for it ourselves. The problem is that when we do this, there's a lot of runtime issues where, maybe to trigger the memory leak, we have to run two commands in a row and then run a third command. We're not going to figure that out when we're looking at the code statically. Instead, what we can use is this tool called valgrind. Valgrind is a really powerful tool that people use all the time to check if there is memory loss in their programs. What valgrind actually does under the hood is it actually wraps the heap and keeps track of allocations and frees, and will tell you like, oh, you lost track of this chunk of code here, or this chunk of memory here. You're never going to get that back. Go look at this line of code to fix it. So to use valgrind, what we have to do is first compile our code with this tacg flag. The tacg flag, what it does is it gives us debug symbols in our code and gives valgrind access to specific lines of code where things happen, so it can tell us where to go and fix our code. So compile it with tacg. You will see that your program has probably exploded to some huge value now. That's good. You want that debug information in your code for valgrind to play with. And then to install valgrind, sudo apt install valgrind. I already did that, so I'm not going to do it, but go ahead and do that for us. And then what we're going to do is we're going to do valgrind tactech leak check equals full pointers and then tac s. What this will actually do is it'll run our program. You see it running here, and then it's going to tell us exactly what happened on the heap and what went wrong. So our leak summary is that we definitely lost 48 bytes in one block of memory. So there is a 48 byte chunk of memory that we did not allocate properly. Oh, 48 bytes. Yeah, obviously. Okay. I was thinking of the previous. I was trying to figure out it was only 48 and not 140 times 4. Anyway, 48 bytes in one block of memory, and it actually will show us exactly on what line that allocation happened. So pointers.c line 30. Let's go there. Struct. Okay. So now we can see that the malloc for our employee buffer never got freed. Oh, right. I deleted that line to show you guys the example. So we can do free employees like this, and we'll do gcc taco, we'll valgrind, and we will see all heap blocks were freed. No leaks are possible. So that is a very high level way of using valgrind to check your code to make sure that it has no memory leaks. Obviously, in production code like this, we'll have to make sure that our code has full coverage, meaning that, in this piece of code, here, there's only one code path for this code to take, right? It'll run this way every time. If we had more complicated code where there are some more conditional statements, it may leak sometimes, it may leak other times. We need to add that logic into it that gives us, full code coverage, that all of our lines of code are running in the order that valgrind expects it. So anyway, that's it for right now. Thanks for watching, guys. Like I said in previous lessons, please take this data, take this information, use it, understand it, absorb it, write some code yourself, get your hands dirty, write some code that leaks, try it out in valgrind, figure out how this stuff all works, and use that to move on to the next lesson. When you're comfortable, we'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroC programming on LowLevelAcademy. You may find this hard to believe, but we've actually covered all of the features of the C programming language itself, right? We've gone over how to make variables, we've gone over how to make structures, we've gone over pointers to those structures even. We can even make arrays of structures, went over arrays in the previous lesson. And we even talked about how to make functions that utilize pointers to structures as their inputs and return some variable. C is a very powerful language, and with great power actually comes great simplicity. There really isn't a lot of functionality in the language under the hood in terms of the syntax. The power of C, and a lot of the examples that you'll see, especially as it applies to Linux, comes from the underlying library, right? So when we write code, for example, right, and here I have my pointers example. When I run the pointers example, I'm writing userland code. I'm writing code that runs in the user level of the CPU, and underneath the user level is the kernel level, right? We don't have access to kernel level code. That's privileged code. If we all had access to kernel code, I could just hack other processes and it gets really evil, right? So we depend on this thing called the syscall interface. And essentially, that's the interface that allows user mode processes to ask the kernel to do certain things like allocate memory, open files, and stuff like that. Now, we could interact with that interface ourselves. We could write code that does system calls and assembly, which gets kind of dirty and really hard to maintain. Or we could depend on a library that already has all the code to handle that interface for us. And if you haven't noticed, when we've been coding, we've been compiling our programs using GCC, right? Now, if you don't know what GCC stands for, GCC actually stands for the GNU Compiler Collection. And GNU, I don't want to get into the history of GNU, but essentially it's an old Unix-like operating system from a while back, and all of the naming of GNU is kind of followed through to the compiler chains of today. But when you use GCC to compile your code, you also bring with it glibc or GNU libc, the GNU C library. You do this by default without even realizing it. And for example, when you use certain functions that you didn't write, but they just do things for you, like printf and malloc, they are all code that is written and already exists in a library that you just get to use for free called glibc, right? So it's really important to understand that when you're writing code in C, you are going to write code that just makes use of the functionality under the hood that allows you to talk to the kernel to do special things like network I/O, like file I/O and stuff like that. And you're kind of up top just managing the memory with the C language. So what we're going to do in this lesson is talk about the way that glibc interfaces with your program, how to read what are called man pages, right? They're manual pages that tell you how these functions behave and how you can find more about the functionality of libc and find different functions that kind of do what you want. So for example, I want to kind of just prove to you here that libc is a part of this function without me even knowing it. So if I type LDD on pointers, what this is telling you is to do linker diagnostics on pointers. And LDD will parse the ELF, which is the file format for pointers. If you don't know, you can type ELF on a file and it tells you what kind of file it is. We've been compiling ELF files. It's the executable and linkable format. Now this ELF, for example, depends on this loader here. It's the LD that comes with Linux. It's the default 64-bit loader. And the loader diagnostics tell me that to load this file, it depends on a few things. The first is the Linux VDSO. Don't worry about that. That's kind of like an advanced topic that came up in the last couple of years in Linux. But the program also depends on, what did we just get done talking about? It depends on libc.so. And that here is the path to libc.so. And what'll happen is when I actually /run the program, LD, or the loader, will get invoked and it will load in this shared object and it will link all those functions together. Again, I did not write printf. I did not write malloc. All of these functions get hooked into our program at runtime by the loader for us. So that at a high level is what libc is. In the next section, what we're going to do is talk about how to read man pages, how to figure out how to use these functions, read the return value, read the error numbers, and all that good stuff. So we'll see you there. Let's figure out how to read documentation, which is really important about libc. See you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today, very short lesson. We're going to talk about how to read a man page. And like I said in the previous lesson, when you're writing code in C, a lot of the time, you're doing code organization, you're writing code that has certain functionality based on what you want your program to do logically, but most of the time, you're going to rely on underlying functionality in a library. In this case, we're using the GNU C library, or glibc, and a lot of the functionality in our code already uses GNU C, or libc. So I'm going to tell you guys how to read a man page if, for example, you haven't read a man page before. So for example, I told you in a previous lesson to get memory from the heap, dynamic memory allocation, where we can get memory that depends on a runtime value. We can change the size of it at runtime. We can use malloc. Malloc is a libc function, right, that uses a system call to get memory from the kernel, and it manages that for us. So to learn more about malloc, we can do is we can type man malloc. Right, so this will open a man page, and it'll tell us kind of a few things about this function. Let me move my fat head out of the way here. So we have a couple things. First, it tells us all of not only the function itself, but the related functions, right? So we have malloc, which gets us memory. We have free, we talked about that before. We free the memory back to the allocator. We have these other guys called calloc and realloc. And then here in the synopsis, we learn about what file we have to include to get access to these functions, as well as the return types. So malloc returns, like we said before, a void star, the name of the function, and also what type is expected in the input, right? We need to put in a size t, which is an alias for an unsigned integer. So we go through here, we can read about the test macros, don't worry about that too much, but what's really, really important is that we read the descriptions of these functions. Again, kind of the mantra of this course is to learn how to write C, but also write clean and fast and safe C, okay? And a lot of the times I find new programmers, they, based on the name of the function, like open, for example, or malloc, they just automatically assume they know what the function does. And like 95% of the times, they're often correct. But it's super important to read the description of a function, because if you don't, you may miss out on some edge cases that you made an assumption about. Like for example, when you malloc memory, the memory is not initialized. That's very important because, for example, if I have memory and I put sensitive data in there, like a password or something, and then I free it, and then I do some other code, and I malloc that same memory for a different purpose, like a string buffer, if I were to print that string buffer, because the memory is not initialized, I would be giving that string buffer with that sensitive password from the first part to that other person, or I could be leaking sensitive information. And then it says if size is 0, then malloc can return either null or a unique pointer value that can later be turned to free. So then that's also a thing, right? If somehow 0 gets put into malloc, we kind of have this undefined behavior, returns either null or a unique pointer. So we have to be reading these man pages and figuring out what's actually going on and what edge cases exist, right? And we'll do one more. The free function frees the memory space pointed to by pointer, the input, which must have been otherwise returned as a previous call to malloc, calloc, or realloc. Otherwise, if free pointer has already been called, undefined behavior occurs. So basically, if you're freeing the same pointer twice, you get a double free. If pointer has been corrupted, you break the heap. And if pointer is null, no action is performed. Okay, awesome. So let's go through and read this next part of the man page, which is also very important, the return value. So again, you may read the function parameter, you may read the function prototype here and say like, oh, I obviously know what the void star is. The void star is the memory that you've allocated. And it's probably true most of the time. But you want to be reading these pages to make sure that you're getting the full understanding of what's actually happening. So the malloc and calloc functions return a pointer to the allocated memory, which is suitably aligned for any built-in type, okay? On error, these functions return null. This is super important. So when you're calling these functions, right, you want to check the return value of any function you call, any and every function, to make sure that it behaved a certain way. And in this case, malloc returns a null if the allocator failed to allocate you memory. It's very important. Null may also be returned by a successful call to malloc with a size of 0, or by a successful call with nmem or size equal to 0. Okay, so again, just be aware that now when we're calling these functions, the return value could be null if something goes wrong. That's really, really important. And then we go through here, and then we have errors. So we'll talk about this in another lesson. This is the error number. We're going to talk about this in the next lesson. And then notes, it's good kind of just to read through these as different patches or security vulnerabilities in libc get updated. Typically, those get annotated as notes that will explain the functionality changes between major versions of libc. So that's it kind of at a high level. Again, I know most of this was me reading a man page to you, but people tend to overlook these. I think it's really, really important that you know that A, man pages are here to help you. B, if you're writing code with one of these functions, just go type man that function and then go read the man page for it. And finally, but most importantly, always check the return values from any function. And when you do, the description of a sane return value is right there in front of you. So with that being said, we're going to use the man page to read about the error number system in the next lesson. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programmer on Low Level Academy. Today, we're talking about the error no concept, or the error number concept. So in our previous lesson, we read a man page for the function malloc. And we read about how, the man page describes the signature of that function, the inputs and the outputs. Now, we sometimes want to know if a function returns an error value, like it fails to perform a thing, like for malloc, as we previously learned, can return null. Why did it fail, right? What could have gone wrong in the function that made it fail? And is it my fault, right? Is there something that I did incorrectly when I was using that function? Now, there's a convention in glibc where there's a variable, it's a global variable, it's called error no, or error number. It's a global number inside of libc. And the convention is that when you run a function like open, for example, and this is me setting up for the next section here where we do file IO. When you run a function like open, one of two things happens, and we can actually I can go read the return value to you, and we can talk about this, as the man page describes it. Again, I'm not all knowing, I just read the man page, right? RTFM. So open at, or create, return a new file descriptor. We'll talk about those in the next lesson. So this is a descriptor that describes a file, or -1 if an error occurred. So one of two things is going to happen. Either it's going to return a good value, the file descriptor to that file, or -1. And now we want to know, like, if -1 happens, if we can't open the file, why can't we open the file? What happened, right? And in that case, error number is set appropriately. And then we can actually read the convention that says if the error number is equal to one of these values, then we can read why it failed. Like, for example, if I, as a non-root user, try to open Etsy Shadow, open will fail and return -1. And I can do p error, which prints an error message string, and it'll say access is denied because the requested access to the file is not allowed, or something like that. I can also say, I can check to see if the file exists, and if we get an exist error, well, then we can't create that file because the file already exists, right? And there's a bunch of these you can read that will tell you the reason why the file or the function failed to behave, right? It's super important that you know how to check these. Let's go through and write some code real quick that shows you how to check this. So this is me skipping ahead, obviously, to the files portion. So we're going to say int fd equals open. I'm going to do a file that doesn't exist, and I'm going to say open read only. And I'm going to say if fd double equals -1, because that's the error value, we're going to say p error open. So what this will do is this will go into open. It'll find the error number. It'll print the error that is associated with that. It'll print it to me, and I'll say return -1, our failure value, right? And then now, obviously, I need to man open, because I need to find the different files and flags that associate with open. Go with this, and we'll include these right here. And I'll do some bad vimming, and I'll include all this. I'll tab all these in. Okay, now let's do gcc taco files.c, run files. Now, again, see what happened? I had the code check to see if we got an error value. That error value was described in the return value section of the man page. And then if it was the error value, I tell the GCC runtime to print the current error to tell me what the problem is, and then to return -1 to leave the program. That's exactly what happened here. We opened it, that file as asked did not exist, and because of that, no such file or directory, and we leave. So that is how you deal with error number. That is what error number is. I hope you learned something here. We'll see you in the next section where we can actually use open to appropriately do file IO, where we can start adding file functionality to our database project. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programming. Today, we're going to be writing some code that accesses files, right? And if you've heard this before in Linux, then you've probably been around for a minute, but in Linux, everything is a file, right? Everything we do in Linux is revolved around this idea of what are called file descriptors. And a file descriptor, as you see here, FD, is just an integer or a number that represents a handle in the Windows terminology to a file, right? So when we go in the future lessons and we open files, we will get numbers put into these variables here that will represent a way of describing to the kernel what file we're talking about. When you write code, by default, there are already 3 file descriptors open for every single program. These file descriptors are pretty interesting because they provide a lot of functionality that exists without you even really having to do anything. The 3 file descriptors are as follows. We have file descriptor 0, which is standard input. It's called standard in. We have standard out, which is file descriptor 1, and then standard error, which is file descriptor 2. These descriptors represent the access to the terminal through the input and the output. That's 0 and 1. And then standard error is another output to the terminal, but it kind of allows you to pump errors in one direction and good output in another, so you can separate them, right? If you want to use like logs, for example, and you want to capture all the errors but not the good output, you can do some terminal foo to make that happen. So when we go into the next lesson, we begin to do file IO. Just understand that all we're getting at the end of the day from the kernel is a variable that will just become a number, right? It becomes a number from the kernel that we can use to describe what file we want to access, right? And as we get into later courses, we're going to have things like sockets. And when we do socket, for example, to get access to the network, the socket is just a file because in Linux, everything is a file. And that number will be stored in this variable that describes the file we're talking about, which is our network socket. So let's move on to the next lesson. And again, to actually write some code that reads data out of a file on the disk to begin our database project. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero2Hero Programming. Before we get going here, I do want to say, as I've said in previous lessons, we are going to start very rapidly stacking the concepts on top of each other. So again, if you're not comfortable with the previous lessons, please, you have access to them, go watch them again. But we are going to start writing code kind of throughout these lessons. We're going to start putting ideas together. And if at any time you feel like you don't understand the syntax of what I'm talking about, please hop in the Discord, go ask me directly. That's what you pay for with this course, is access to people that have taken the course or that are in the course. But then also go watch the lessons again and make sure you understand it so that you get what's happening in the code. I would hate for you to get to this lesson, try to learn about file IO and like not understand what an array is when I'm using it, right? So just understand that. And if you do feel ready to go, then let's dive right in. So in the previous lesson, we talked about, when you're accessing files in C, you get these things called file descriptors, right? And a file descriptor is literally just a number that represents to the kernel a file that it has opened for you, right? Via a syscall, which is given to you through libc. I know a lot of words are stacking up here. So when we want to open a file, we are going to just open with this file with a function called open. And again, when we are writing code in C, we want to make sure we keep these man pages open so that we can read the descriptions of these functions, right? So here we are talking about the open function, and the open function takes in a parameter called path name. That's the path to the file that we want to open, and then an integer flags, right? And this describes the kind of access that we want to the file. Like for example, if we want to open it in read-only mode, maybe we have a read-only file. Okay, we can tell that in the flags function or in the flags parameter. If we want to open it append, meaning the file is already existing and we're adding to the end of it, then okay, cool, we need to specify that in flags. Okay, well, where are flags defined? Flags are defined later on in the function here. So we can say read, write, and we can also do things like create if the file does not exist, or we can do clone exec. There's a bunch of flags we can do here. There's a fuller description of the flags in the man page, so go read them if you want to learn about all of them. But today, for the purposes of this example, we're going to be using the read, write, and create flags. So we'll do read, write, and create. So create creates the file, and then when we create the file, we open it read, write. So we'll do this, and again, we have to include the header files from the man page. So let's go and check that out. We just copy these and put them into our code because this gets us access to the function. So we'll do open, and then we'll say, my file, and I want to do o read write, and then o create. Now the question is, how do I combine these flags together, right? Flags are typically bitwise values, and we'll talk about that in a future lesson about data operations. But when I want to combine two bitwise flags like this, I do the OR operation, right? A binary OR essentially says take A, combine it with B, and return that value. So by ORing these together, we are using both of the values. And again, as usual, if for some reason fd equals -1, like the file doesn't exist or it's not the right permissions, we print the error of open and we return -1. Right now, we have no other cleanup code to do, so we'll just leave the program. Now, my file is kind of boring, right? Maybe we don't want the myfile file to get created every time. I want to specify a name of a file, right? So what we'll do is we'll change this, which is a character pointer argument, to be a new thing we'll talk about in this lesson right here. We've been avoiding the arguments to main for a while. You may have seen other arguments in other lessons or courses you've taken. There's actually a bunch of arguments that main takes when it starts up. The arguments argc and argv represent the number of command line arguments and a vector of command line arguments that are given to the program on the command line, right? So if we want our program to be something like, we type my program and then file.db, right? This file.db will actually populate in the argv1 parameter. So we'll do argv1 here. But we also need to make sure that if we're accessing argv1, that argc is set to 2. We need to make sure that they actually gave us 2 arguments. The first one being the command line name of the program, but then second, the argument itself. So we'll say, if argc does not equal 2, we will print the usage of this program is to type the command and then say the file name. And the %s is going to get argv0, which is always the name of our program. We return 0. So let's go ahead and compile this. Okay, so we did not give it the argument. Files file name, so we need to give it a file name. Cool, so we'll do my new file.db. Okay, so we did not get an error, which means that in theory, this file was created and it was opened. Awesome, so let's go check that real quick. And my new file.db is created and open, but it's all red. What is going on here? Hold on. Oh, yeah. Sorry. For open, you also need to specify the permissions of the file. So right now, by default, the permissions are just this random number. This number was likely the argument that was on the stack. And because I didn't specify one, it just gave it this random value. So we'll go through and we'll make our file be O, which is octal, and then 644. So this gives me read-write permissions, and it gives people in my group and people that aren't in my group just read permissions. So that's kind of like the default go-to for non-private files, right? So GCC, and we'll do files, mydb, permission denied. Okay, we have to actually remove this file, and I can do that. Good. And then finally, we'll do make my new file. Good, it's there, and we'll cat it, and it's an empty file. Awesome. Okay, so now that we're through that fiasco, let's actually do what we want to do in this lesson, which is write to that file. So how do we write to a file? Well, we probably man the write function. Wow. So here is an interesting thing. If we use the man function or the man command on words that are Linux commands first, we have to do what's called man2, right? Which gets us the page for libc. So if you ever find yourself like man open or man write, and you get to that other page, do man2 or man5, and you'll get to the right page. So here we have the function write, which takes in our file descriptor that describes the file we want to write to, a pointer to the buffer that contains the data that we want to write, and then the number of bytes that we want to write, so the count of those bytes. And then it returns the size t, which will read the return value. On success, it returns the number of bytes that are returned. Okay, awesome. That's easy enough. Let's go try that real quick. And we have to include unistandard to use this function. So we'll go through them, copy that in. Awesome. So now that we have the file descriptor open, and we've checked that the file descriptor is the correct file descriptor, well, first we'll make a buffer. We'll say char star my data equals hello there file exclamation point, is we will write to it. We'll say write fd, which is the file descriptor to our file. We'll write my data, which is the number of bytes that we want to write. And then the count of the bytes is the string length or strlen of my data, right? So this is the number of bytes that exist in a string, which is how many bytes that we want to write. And then to use strlen, we need to pound include string.h. Very good. And then what we can also do is, no, we'll do that from right now. And after that, we will have to do close on FD to close up the file descriptor. And then we can just return 0 for happy, healthy success. So we'll do GCC to compile that file, and then we'll do ./files my new file, and we'll cat this. There we go. So now the data is in the file. How cool is that? So what have we done today? We have gone into C, we have written code that takes a parameter from the command line, opens it, it writes some data to it. So then we close the file and then we go from there. We'll take a file and we'll read data from it and then use that to kind of configure binary data. And we can even read that into a structure, which is where we're going to get really, really cool for the database project. Let's dive right in. We'll see you next time. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. So last lesson, we got a little dirty with our hands. We were able to write some data to a file. Pretty cool. Now, what we're going to have to get comfortable with is reading data from a file. And it's important to understand that in our database project, the data itself may not be all string data, right? In our previous example, we wrote a string to a file. But when we're reading these binary data blobs, like a database file, a lot of it's going to be binary information. And the power of C is that we can kind of arbitrarily convert one data type to another. And we're going to show you how cool that is in C. We're talking about the database header structure that I have here. So again, in module 12, we'll actually build this thing out. We'll do full project planning on how to build this thing. But for here, let's say, for example, we have a database header type. And in that header, we describe three things. We describe the version of the file type that we're using. So we can define our own file type version. And this is version 1, for example. We can then also say how many employees does our database have. That'll kind of allow us to describe how far we can iterate into that file. And then finally, the file size. Maybe the file got corrupted. So if the header says it's one size and the actual file size is another size, we know to do some error checking, right? Now, we can store all of this into a database file, but we need to read that data into a structure so we can actually use it and edit it so we can write it back down to disk, right? So what we can do here is first we want to read this data from our file. And so here I've made this database file, right? This is a database file that contains some binary data. We want to read this data off of the disk and then tell us the information about it as regards to our header structure, right? Because we're going to have the version, the number of employees, and the file size. So what we can do here is call the function read, and we're going to man read real quick. Let's go read what read does. So we can specify the file descriptor to read from, the buffer to read into, and the size t to read. Now notice that the buffer to read into is a void star. That means we can give it any pointer type to read the data into. And because the header of the file is represented by this binary data here, but more importantly, the structure here, we can create a buffer that is that structure itself and just read right into it. So we'll call this struct database header t head. And then we're going to read from the file descriptor into the address of head, the size of head, right? So this will read that many bytes. And we should make sure that read, which returns the number of bytes read, if it does not read the size of head, then we have to print the error that read had, right? Same as before, p error read. If we have an error, we have to close the file and we have to return -1, right? And then otherwise, if we get to this point where we've read our database header into the header structure, we can then print the information about the database, right? And head.length. Let me go read the names of the variables real quick. Version employees file size, not length. And then at the end, if we get that correct, we close the DB, we can go from there. GCC the files, no errors. So we're going to read this in. I crafted my database file incorrectly. I'm sorry, guys. Okay, there we go. Again, I'm doing this by hand right now before we actually get to the creation piece. Cool, so yeah, there we go. This is what I wanted it to show. We have database version 1, the number of employees is 65, and the file length is 8. Right, so what we'll do now in our next lesson is we will do a check on the metadata of the file to make sure that the file metadata reported as the input actually matches the metadata of the file, right? So we need to figure out like how big is this file? It says 8 bytes and the header says 8 bytes. So we got to make sure they match. We'll tell you how to do that in the next lesson. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. So again, in this section, combining a lot of ideas, using functions from libc, we're checking error numbers, and essentially, we're checking to see what the data reported from a file is as input to a structure, and use that to show different kinds of data like the version of the database, number of employees, etc. Again, the mantra here is that we're writing code that is not only effective, but is safe as well. And it's really, really important that as you go forward programming, whenever the user gives your program data, it's expected that data is malicious in some way, right? Obviously, not all data is malicious, but you should treat it that way. You should expect that malformed data can come in and decode defensively. So an example of doing that is when the header of the file says the rest of the file size, we want to verify, is the actual size of the file on disk the same as what the header reports it is? And if it's not, we close out of the file and we get, move on with our lives, right? So to check the metadata of a file, we're going to run a new function that exists in libc, and that function is called stat. Now, stat is actually a Linux command. We can do stat on our file right now on the command line, for example, to get some good information. But we want the C version. So again, if we do man2 stat, we get the actual man page. Now, stat, the way it works is there are three different kinds of stat. There's a stat with a path name that you can just give it the full file path to a file to stat. What we want to do is run fstat, because fstat takes in as input a file descriptor, and we already have a file descriptor that is open. And then what that'll do is that will populate a stat buffer, which is a buffer that contains a bunch of really juicy information as described here about the file. And specifically, we want to check the st size, or the total size in bytes of the file, right? And confirm that it matches the header information. So to do this, what we're going to do is we're going to go into our code. Well, first of all, we have to steal the header information. So we're going to take all of these, and I think we actually have all of these already. We'll go check real quick. We have stat, we have unit standard, we have type, so we're good. So what we're going to do is we're going to say struct stat header stat is equal to 0. So we're going to zero out enough room in the form of a stat structure for information about the header file. Or actually, we'll do db stat. Call it db stat. Cool. And then so once we get the file length read out of the file and printed, we want to do is do stat on fd to the db stat location. Again, stat takes a pointer to a stat buff. So what we're doing here is giving the address of the stat buff to stat, and stat will fill it out for us. Now again, any function that we write, or any function that we use, we want to check the return value. Let's go through and check the return. You can't search man pages, big sad. On success, 0 is returned. On error, -1 is returned. So what we'll do if stat is less than 0, we'll p error stat and be on our way. We'll close the file descriptor and return -1. And again, the chances of us actually getting a bad stat are low. This could be a case where like the file descriptor, is closed and we call stat on accident. It'll reflect it there, but this should go through perfectly. And then what we want to do is we want to say db file length reported by stat, and we'll say %u again. We'll do, it's the dbstat.st size, right? That's the field, and I got that information from our stat man page, and it says right here, st size is the size in bytes. Awesome. So we'll go through from here, we'll hit Q, we'll GCC. Getting a couple warnings here. Oh, right, I'm not calling stat, I need to call fstat. See, that's me thinking that I know what a function does, but it's actually the wrong function. And again, always listen to your compiler when it throws warnings. The warnings are probably correct. It's very bad to ignore compiler warnings. %u expects unsigned int, but this is an off t, which is a long int. Okay, so we have to give it the L parameter in the file here with GCC. I gave it to the wrong one, sorry. It's not this one, it's this one. There we go. Again, programmers are human. I make mistakes. There we go, no errors, perfect. We'll do files on my new file DB, and it says DB file length as reported in the header is 8, but as reported by stat, It is also 8. Good. So this means that we have a sane database file. What we want to do is be a little defensive in our coding, and we can say, we'll say if dbstat.st_size does not equal head.filesize. We'll say, get out of here, hacker. And then we will do our procedure. We'll close the FD and we'll return -2. This is a really evil return value. So we'll do that. We'll GCC files. And again, we're not going to get a bad file here because our file is sane. What we can do is we'll do my echo command to build my fake file. I'll give it a 9, right? So the file length is still 8 bytes, but it's going to report in the header that it's actually 9 bytes, which is not correct. So we'll see how my program behaves. Let's see. So it caught that these are different. Get out of here, hacker. So that's how you check your file metadata. Again, if you want to learn more about the metadata that you can retrieve from fstat, you have all of these goodies that are here in the stat buffer. Go through, play with that, and start to scaffold out, write some code that opens a database, that opens a file and makes use of it. And we'll move on to the next lesson where we start really, really digging down into the C language and getting ready for module 12, where we write this whole thing and put all the ideas together. I'm getting excited, guys. We'll see you in the next one. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programmer on LowLevelAcademy. In previous lessons, we talked about the features of the C language and how to make things happen logically, or how to organize our memory structurally to make our code do what we want. But we did jump over a pretty important idea, which is the idea of variable types. And I know in a lot of the examples, I used this thing called an int, which is an integer, and I kind of just glossed over what this actually means. So when you declare a variable, obviously, like we talked about in the variables section, you give it a certain type. And this integer type is a type that can store a number. But there are actually a ton of modifiers and other types that allow us to change kind of the purpose and the size of that variable. So in C, there are a bunch of basic types we'll lay out here. We have a character, a short, an int, and then a long int. And all of these vary in size. And obviously, if we want to use these, we would give them different names, so like, char y or short s or int I or whatever. We would give them proper names, and these would all contain variables that have different lengths. So if you weren't already aware of this, and we'll call this L, for example, the character type by default is a single byte, or that's 8 bits. A short is 2 bytes, and that's 16 bits. An int by default on 32-bit systems is 4 bytes or 32 bits. This may vary. I'll tell you how to figure out what actually the proper size is in a couple seconds here. And then the modifier long is actually, historically, when you said long int, that actually upgraded it to 32 bits on older systems. To make this now an 8-byte or 64-bit variable type, we say long, and then apply that to int, and we call that variable L, for example. And then finally, we want to talk about this thing called signedness, or if the number is signed or unsigned. So by default, because we haven't put unsigned in front of the variable, that variable is signed. Now, what does a signed variable mean? Well, right now, the integer x we have up there, I'll make another one called int xx, can represent any number to include negative numbers that falls within a 4-byte type. So for example, I can have int double x equal -4. If I were to create a number that is an unsigned int xx and set it to -4, this is actually invalid. This would compile, but it would throw a warning that I'm trying to put a negative value into an unsigned integer. Now, you're probably asking, why would I want to make a variable signed versus unsigned? When you have a signed variable, you actually limit the amount of numbers that variable can represent. We're going to talk about that by talking about the bitness of a signed or unsigned variable real quick. Going into Photoshop, we'll do a little bit of drawing. So before, for example, I said that a character was an 8-bit value. So we'll draw out my character C, and we'll write that out there. Now the character internal to memory is, like I said, 8 bits. That's going to be 1, 2, 3, 4, 5, 6, 7, 8. That's 8 bits of memory. Now, what'll actually happen is, because this variable is signed, I have not put the unsigned modifier in front of it. What the compiler is going to do internally is use this first bit here to determine if the variable is negative or positive, right? So because of that, because we're using this variable to denote information about the number and not the number itself, we limit the range of what this number can represent to about half. So for example, a signed character can represent from -128 to 127. And that makes sense, right? Because these bottom 7 bits can represent numbers, and 7 bits can go up to 127. And if we enable that 8th bit here, we turn that number into its negative most value. And this applies to every signed number. The signed int x can only represent up to half of 4 bytes. So we'll see what the math turns into real quick. I don't have those numbers memorized. So we'll do 2 to the power of 31. So it can represent up to, or it can represent negative this number up to this number minus 1 positive. So it's 241 million, but it's this minus 1. So this is the maximum representation of that number in a signed integer. And again, if we want to produce the maximum amount of size that this number can represent, we apply unsigned to it, just knowing that it can no longer represent negative numbers. And talking about numbers, we also have different ways we can represent numbers. As you've probably noticed, none of these variable types can actually contain decimals. There's an entirely separate type for that called a float. We'll say float f, and it could say it equals 3.14. Now, the accuracy of this number is actually pretty low. You can only get out to a certain number of decimal points of accuracy with this. What you want to be using is instead a double, which has much more bits of accuracy. I believe it's out to like 21 bits of accuracy, 3.14, 159, etc. Right? So these are all the variable types you can represent in C. There are some more custom ones that you'll see come out in the Unix standard libraries, like size t, for example. But a lot of these variable types are actually just aliases of other types. So go ahead, play with these a little bit. Go write some code that uses a short, for example, that uses a long int, and just see how they feel in the compiler. And we'll see in the next lesson where we talk about typecasting between these variables. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about typecasting, which is this concept in programming in C where we're converting one type of information to another. We're telling the compiler to regard information in one way and then telling it, no, actually try to regard it this way instead. So let's walk through kind of a couple of examples of that and how this applies to us in C. So for example, let's say we have an unsigned int x and it's equal to 4, right? Well, now let's say we have some logic that goes on and then eventually we want to create a new variable that is equal to x, but instead of it being unsigned, it's signed. So what we'll do is we can say that int, we'll call it signed x, sx, is equal to, and here we're doing a typecast, which is we are telling the compiler to treat everything to the right in the following expression as this type. And we're going to say cast it into an int, and then what are we casting into an int? We're casting the variable x into an int. Now, this is an interesting cast, right? Because we are converting a variable that is of the same size, but a different type, right? So if this, for example, had an exceedingly large number that was over the value cap of a signed integer, you would have some weird logic happen where it would convert it to a negative number, right? So that one's not so interesting. But let's say, for example, we have another integer case. We have an unsigned int, we'll call it big X, and it's equal to hexadecimal FF, FE, right? So this is the number, and this is very large. This is almost at the cap of an integer, right? It's almost up to 4 bytes. And let's say, for example, we had somewhere else in the code where we needed to create a short that was cast out of big X, right? It took the information in big X and created a short. So we'll say short kinda big is equal to the short casted version of big X. Now, this case is interesting as well because we have a type that is 32 bits and we are casting it into a 16-bit type. Now, because we are explicitly asking the compiler to do this, it will allow us to do this. However, it's probably going to warn us that we're cutting off the top 32 bits of information because we are asking 32 bits to get stuffed into 16 bits. We are inherently going to suffer some kind of information loss. So it's important that we're aware of that when doing this type of typecasting. Now, let's say, for example, we had the opposite thing happen. We had a variable that was, let's say, a signed short. We'll say, let's call it short2, and it's a -1, right? And now we're going to upcast that from 16 bits to 32 bits using a cast to a signed integer. So we'll say int was a short, and it's going to be equal to the int cast of short2. Now, the reason this case is interesting is because what's happening here is we are taking a signed variable, and again, in binary right now, this variable is set to FFFF, or all ones, it'd be 16 ones, and we are casting that into an int. Now, the int is 32 bits, and the short is 16 bits. So you might think that there's actually going to be an information hole, right? There's going to be a variable that's created that's 1234, 1234, because we are just pulling in the short and expanding it to the left. Well, actually, because they are both signed variables, what's going to happen here is what's called a sign extension, where when we create this extra room for this new variable, it's going to slide out that leading one to make the entire variable negative. So this variable will actually become all quad f's because it's casting the negative value from the short and expanding that into 32 bits. Also pretty interesting. Another one we can do is something like this, where if we have float f is equal to 3.14. Now, we can make a was a float and cast that in from f, right? Now, if we have was a float and we say that we cast f into an int, what's going to actually happen here is there's going to be an assembly instruction that will convert this 3.14 into the nearest integer value, and that will make it a 3. So we're essentially rounding the float into an integer. So that's kind of interesting. And then finally, the one we've done before, I think when we talked about malloc, was typecasting pointers to and from each other. The reason this is interesting is because, for example, if you have a character pointer, which is a type, right? And we want to cast that into a short pointer, we can do that pretty simply. We can say that, short pointer my data is equal to, we'll say argv1, cast that into a short pointer. And essentially all we're doing here is we're saying, hey, take char pointer argv1 and treat that like a short pointer, and that can assume that there's binary data we want to look at, or maybe there's Unicode data there that are all shorts and not actually ASCII. So again, not super important for the project at hand. I just want to let you know that this is a feature of the C language, where if we have data that is one type and we want new variables to exist that use that information but as a different type, this thing called typecasting allows us to transfer that information from one variable to another. We just need to be aware of the implications of when you have two things that are like the same size, or you're downcasting to a short, or maybe you're upcasting to an int, or maybe you're crosscasting. You're casting from a variable that is a float into an int. So again, just be aware of all these different edge cases of typecasting, and we'll see you in the next video which is how to do more advanced C programming with bigger C files. We'll see you in the next lesson. Take care. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgramming. If you look at the code that I have here, I'm actually doing a bunch of stuff in not a lot of lines of code. And the way this is possible is that, like we've talked about before, I'm breaking out a majority of things that happen in my code to functions, and the functions do one specific thing. So for example, this function here opens a file by file name read write and returns to me the file descriptor. And then I use that file descriptor and then I use it to parse a file header, and it outputs to a integer pointer the number of employees in that file. What I've done is kind of created my C in a way where I can abstract away a lot of the functionality and just expose an API to me as the programmer to do simple things. Now, when we have multiple APIs that take on, a lot of functionality, like one is for the files themselves, opening the files, checking file properties, seeing if the file is structured properly. And then the second part maybe is I'm parsing out specific database information. I'm creating one of these things called modules. And a lot of this gets into sane project design. So let's talk about how to design a multi-module system in a way that we don't create spaghetti code. So if I like to think about things when I'm programming visually, right? So if I have this big circle down here, I picture like this is my main function, right? And then down here is like me as a user. I'm sending in things via standard in, and I'm pulling things out via standard out, right? And then atop the main function are these modules, right? So like I said before, we have maybe this one here, which is the file API. And then this other one over here is like the parsing API. And then maybe in the future, in future lessons, I incorporate the networking API. This is a separate module here. What we're doing here is creating a design where I expose these things called interfaces to my main API that allows the program to become very simple. So like I said before, here I expose an interface, they're called open read write. It opens a file read write, and through this interface comes a file descriptor, call that an FD. And then I can push that FD to another API, and it returns to me some other variable, right? I'm enabling myself to design this in a way where the interfaces that I use are very, very simple. Now, you've probably heard this thing before called spaghetti code. So what does spaghetti code actually mean? Like, what do people mean when they say, oh, this code is spaghetti, I can't follow it? A lot of the time, spaghetti code comes from this idea where these modules are unnecessarily coupled to each other. So for example, I have this main API that interfaces with file, and all file does is goes out, it reaches to a file, maybe it returns a file descriptor or returns a size or something. But what if the file module also depended on the parse module? What if the file module called into parse via, like, when it opened the file, it also parses the file too? Well, that becomes very logically hard to follow if I have to debug my file module, but also, like, if these two are required of each other, if they're coupled together, why not just make them one module? Why not just make this whole thing one block, right? So spaghetti code is this idea where code is kind of just this blob, it's this mess where it's not organized logically, and it's hard to discern what piece of code has what functionality. So that's code design at a high level. Let's walk through how this actually works in C and how we can make it happen in our compiler right now. So here I have the code written out, and you'll notice there are a few new things we're adding to our code that allow us to do multi-module programming. I have made a video about header files, so go watch that video. It's in the content down below. Go check that out. We'll talk about it here as well. To use the functionality of a different piece of C code, like we talked about before with glibc, we have to expose a header file. And what that header file contains, so we'll talk about the open file read write, for example, is it exposes a declaration of the function we want to use, because the compiler is going to be aware that we didn't write the open file read write in this C file. It's going to look in the initial C file that you're in and look for that function, and it's going to say, hey man, I don't know what you're talking about. And the way you avoid that is by including not a definition, but a declaration of that function here in a header file. And the header file also has these things called header guards. Essentially, all this does is it prevents you from declaring the function twice, because if you have a duplicative declaration of a function, the compiler will be like, hey, you said this thing exists in two places. How is that possible? This prevents you from doing that. So now, inside the C function for main, we are going to use what at this point, at this stage in the compilation process, is an anonymous function. It exists, but it has no definition. Then in the C file for file, we're actually going to define that function. So this in the header file is a declaration. We declare that it exists, but the file.c, that file, that source code, will have the definition. And then note that also inside of this, we also include the header file. This allows us to include any other information that are like maybe public structure definitions or constants or stuff like that. But here we go ahead and we actually define that function. So when we do the same thing for the parse functionality. In the parse.h, we define a structure that is used in the code. We also expose the declaration of that C function, but then we actually write it in the C file. So that's how we use the functions in C. That's how we write multi-module C programming in C. But now, how do we define it? So here we're taking a look at a pretty well-organized structure for a project. We're at the top level of the structure, right? So we have three main folders. We have include, which is going to include all of our header files. And again, it's called include because to use a header file in C, we use #include. It's going to have our source files, which have our definitions, all of our defined functions to include our main. So we have all these files here. And then finally, we have the bin folder, which is the binary folder. This is the output of our compilation process. So to compile this code, we have to do all of the initial compilation steps before we link the program together. So we're going to talk about how to do this automatically in the next lesson in our build system section, but to do it right now by hand, it happens the following way. So we need to invoke GCC. We're going to tell it to output, for this case, we'll do it manually one by one, the file.o object. This is an intermediate object of compiled code that is not linked. So we'll say file.o. We need to tell it that the include path to the files that are going to be specified in the include header right here are in the print working directory. So this is like a command substitution. We'll do print working directory / include. That gets us to this folder here. Then we're going to use source/file.c. And then finally, to make it only output an object file intermediately, we'll say, hey, don't link, only compile with the C flag. And now you should see that a file.o pops up, not a file.c or a file.a, a file.o. And if you type file on that file, it should be a LSB relocatable. And we're going to do that for every module we've created for our C program. This will be the same thing. It'll be parse.o, and we'll say to compile the parse.c library, and that will produce a parse.o. And then same thing for main. Main.c, and we're going to output a main.o. Okay, so now that all the files are compiled, we have created the intermediate objects before the linker stage. Now we need to actually link these files together. And the way we do that is you say GCC, we're going to link all of the .o objects, and we're going to output bin/new out. Okay, what this did here is this took all the intermediate objects, it linked together all of their functions, and it turned that into a new binary. And what we can do is we can now test that binary, new out, and it's going to ask us to specify a file name. We're going to specify myfile.db, and here we have the program actually running as intended. So begin to wrap your head around this. I know it seems a little complicated, but if you can organize your code in modules that are a little more sane than my current diagram, but just look at the red coloring, right? These ideas here, a main with different parts that are not coupled together, they're separate. You can organize your code in a way that is easy to follow and easy to debug. And then when you compile it, you have the compiler compile each one individually, but we'll figure out how to do that automatically with make in our next section coming up. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Now, I bet you didn't know this, but when you bought this course, you're actually getting a crash course in 2 languages. One is C, and this next one is a little less fun, but it's make. So if you've ever installed a project pretty much anywhere, you've probably ran like configure and you did something, and then eventually you ran this program called make. Now, what make actually does is it goes into the make file in the current directory and executes the script against whatever target you specified. And for example, here, the target by default is default. So if you don't specify a makefile target, it'll go forward and it'll run the makefile default target. So let's walk through step by step and got to talk about the syntax of what a makefile is, what's going on here, and just I want you guys to go forth and play with makefiles a little bit and use them to automate the process of not only building your tools, but testing them as well. So when we have a rule, this blue part on the left is called the name of a rule, right? So when I say make X, it'll do the X rule. So by default, it runs the default rule. Now on the right side of a rule is the thing that needs to be built for the rule to be considered completed, right? And it's considered the target of the build. Now, here we have a $sign in parentheses, which is a make variable, right? So it's going to evaluate the variable that I have here, which is the bin final program. So the default target is to build our final program. And in make, what we're kind of doing now is we're going to walk down this like recursive path of targets, right? So if this is the next rule to run, we're going to go find the rule to build our bin final. And here is the rule, it's the target rule, and what is required to be built for this rule to be considered complete. We need to build all of the objects, right? And if you remember before in our previous lesson, what we did is we had to go through manually step by step and manually compile each, .c file, like a source.c, into a .o file by hand. What we were doing is we were compiling a source file, as you see here, into a object file, which you are seeing here. So what this rule does is it says to build the target, first we need to build all of the objects, okay? So what is the object list, the list of objects defined as? Well, we're doing this thing in make called a pattern substitution. We're taking all of the source files, which is defined here, so everything in source.c, we're converting that into object.o. Okay, and then we have this final rule that says to convert a source.c file into an object.o file, we run gcc tac c, and this little symbol here means the input file. and we're going to output the output file, right? So we're going to say for every source.c that there is, compile it, and then output the object.o. What that will do is that will tell make that the list of objects is complete, and then allow us to run the rule for our target binary. We'll say gcc tac o, and this $@ means the output file, so our target, and this $? means the list of our input files, right? So what we're doing is we're walking down this recursive tree of targets and rules, running them, and then walking it back up to eventually complete our rule. And then also a fun rule to add is the clean rule, which eventually says if I type make clean, it removes all of our objects, it removes all of our binaries. So let's go forth and test this real quick. We'll do make clean, and you'll see it tries to run the script that I have. It removes all the object files, it removes the bin/star, it removes any possibly completed binaries that we have. And then I'm going to do make, and it'll by default run the make default rule, but I'll show you that just by typing default as well. So what it did is it went into our source tree, it found every source file, it replaced source with object and .c with .o, and then it compiled it and produced that object file. And once every object file was created, it was then able to run the target rule to compile all of the object files into our final binary, and we can test that with bin final on my database, and it outputs the same thing it did before. Make is really, really powerful. Please go write a make script. I'll put this make script in the content section for the text for this lesson, but just mess around with it. See if you can get your own multi-module programming to compile and test in Make. And we'll see you in the next lesson where we talk about making your own shared object libraries. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgramming. So I know a lot of this section is talking about kind of like program organization and how to write code that uses multiple functions or multiple files and doing it in a way that makes sense, right? So in our previous section, multi-module programming, we talked about a lot about if we had this main blob here, which is like our main program, we were to design these other sections on top that were considered modules, like the file module and maybe like the net modules over here. And these were not coupled together because otherwise that's spaghetti code and that's bad, right? Now, in the example we had before, each one of these kind of came from its own C file, right? So this was like file.c, for example, or maybe this was like net.c. Now, what if we wanted to use this code over and over and over again in multiple programs, right? We wanted to have this code duplicated across multiple programs with the same functionality, we wanted to use it multiple places. Well, this is actually what is referred to as a library, okay? And we're going to talk about today how to write code in C as a library and how to transport it from one program to another and to include it in your code. Now, there are two kinds of libraries in C. There's one that's called a shared library or a shared object. It's a .so, so we'll call it a shared object, or a static library or a static object, right? And like I said before, this is a .so, and you may have seen these are a little more rare. It's a .a file, also referred to as a .archive or an archive file. And the primary difference between the two is that when you run your program, in the case of a shared object, what's actually happening here is your program runs in this little blob here. This is what is called your ELF, your executable and linkable format. And this is just the code that you wrote. So I'm gonna put U for your code. A shared object gets loaded outside of your ELF. They are separate ELFs in the same memory space. And the loader will build a link between the two at runtime that tells your code how to get to the ELF and vice versa. That is a shared object. And an example of this we've already talked about actually is glibc, right? Glibc runs as a shared object. You can compile it as a static object, but the default case is a shared object, right? And then again, that is a .so file. Now, the difference between a shared object and a static object is where it gets compiled. So the shared object actually gets enabled at runtime. Your program specifies that it needs it, and that's put in at compile time. But the shared object gets loaded into memory at runtime. Whereas a static object, what's actually happening here, is that all of the code gets ran in at compile time. So before, remember we talked about how we had these intermediate objects called .o files, where I had like main.o and like file.o, right? So we'll have file.o is one elf, and we'll have like main.o is another elf. Well, this static library, which is a .a, literally all it is a bunch of elves that are pre-compiled, a bunch of .o files compressed into some kind of compression algorithm into an archive, right? So if I have glibc as an archive file, what it'll look like is libc.a, which is also another just intermediate object file. These are another elf. And when we get to compile time, what'll happen is the linker will take all of our elves and make them one elf, where just one corner of it is the .a file. And when it gets ran at runtime, all of the code exists in here in this one blob, right? The primary difference is that one happens at compile time, that's the static object, and another happens at runtime, that's the shared object. The difference being, and the pros and cons being primarily that a static object will increase the size of your binary and duplicate code may be running at the same time in different locations, whereas a shared object will always exist in one location, but it could get shared across multiple programs. So how do we do both of these in C, right? Let's go make a shared object and a static object. So here I have my main file, main.c, and we're going to use my favorite library that I've ever written in my entire life. I'm making it for you right now in front of your very eyes, libthe. And what libthe does is it just executes the functionality in a library, and the function is called function in a library. And despite, if you're using this as a shared object or a static object, regardless of how you're using it, because this function is not defined in this C file right here, you have to specify the header file for libthe. And if you're using any library, a good library producer will give you a header file that will allow you to compile against it. And in libthe, again, we just specify the declaration of our function. Now, to compile our own code as a static library, all we have to do is first compile the binary into an intermediate object like this, like we did in the previous example. We'll do archive rcs, we'll create libthe.a, and we'll input libo. So now we've created a libthe.a that we're going to use to put into our previous file. And then to include libthe.a, all we have to do is move that object to our immediate compilation folder. So we'll say move libthe libthe.a to here. And then to compile it against our main file, which again uses that functionality here, all we have to do gcc tac-o, the name of our binary. We have to do the name of the C file and the archive file here. And we also have to include the include directory, which lives in libthe. And there we go. Oh, it's libendf. There we go. Made an error in my header file. Okay, and compile that. Boom. And then we say tehe, which is actually the functionality of our library. That's all it does. It just prints out that we're in a library. But that's how we include code as a static library. Let's compile this now as a shared object. So again, this one is a static object. This gets put into the compilation process and is built into the elf. Let's make one that's a shared object that gets ran at runtime. So we'll do remove this to get rid of it, make it a little less confusing. Go here, remove the .o and the .a files. So to compile it as a shared object, what you do is you do gcc, and then you produce not a .o file, but you say you want to create a .so file. So we'll call it libthe.so. We'll do tac shared. So now we have libthe.so. It's a shared object. We can do file on this to confirm that it is a least significant bit shared object. And then now we want to do is move this one level up so that it's local. And so to compile this one, instead of doing it with it in the current directory and saying, that file, we want to say we want to link against a library. And we don't say the full path of the library. We just say the name without libs. We do tehe. So it's going to say that it cannot find this directory. It cannot find this library. And that's because we have to specify a library search path. We could say tac capital L is the print working directory to enable that. And there we go. Now we can do this. Now what is going to happen is when the linker goes to run our program, it tries to search for where this library is. And because it's not in like /user_lib and /user lib64, it's going to be like, hey, I can't find the library. Where is it? So to fix this, what we do is we say that ld library path is equal to LD library path. And this variable is just the place that it looks for libraries. We add a colon and say also it's the current directory, pwd. And then we say our program main. And there we go. So what that enabled it to do is look in the current directory to find our library, and it found it here and it linked it at runtime, and the program ran from there. If we wanted to actually install this library, what we would do is we would move it to the proper LD library path. Let's move libthe.so to user lib, and there we go. From there, we will run main, and it finds it automatically. So that's how you break up your code into library files. You can do one as a static, one as a shared, whatever you feel like you need for your program. But what we're doing here at the end of the day is making it so that our code is not only understandable and organized in a way that's sane, but now it's shareable, right? We can take our file.so or our libparse.so and give it to other projects that we're doing or other people that are using our code, maybe make it open source or something like that. All right, guys, and that is it. So we are going to move on to the next section and begin the full design and writing for our employee database project. I'm looking forward to it. We'll see you guys there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today, before we actually dive into the employee database project, which we finally made it to in this section, section 12, we're going to talk at a high level about design, right? How the code is going to look, the features it will have at a high level, which will enable us to write the code without going back and constantly refactoring it, right? Before you start any major C project, you want to have kind of a general idea in your head about how it will look and the functionality it will have under the hood before you write any code, because otherwise you may catch yourself realizing new features about your project, and then you have to go back and fix them over time, and that will waste a lot of your time when you're coding. So the whole idea here for this project is we are going to have some kind of employee database, right? What will happen is before our program is written, the employee database will just be some file on the disk, right? And it'll have entries inside that database. And what our program will do is when we say, we'll call it dbview, it's going to be the name of our program. This program will read the database project, and it will cascade all of the entries, all of the employees in the database into memory, right? So it'll create a list in memory that will contain all of the employee structures. And again, structures we learned about in a previous lesson. They're just memory that's concatenated together. So we'll read the employee database. We'll make sure that it's valid, right? We'll validate the security of the file to make sure it's not fake or it's not missing any critical information. And then we'll read all of the employees into memory. And then based on the flags provided to the program, we will do some kind of functionality, right? So for dbview, if we say, tac A, we're going to add an employee to the database. And that employee will be specified by a string, and we'll kind of specify the string in a future lesson here. We could say tac D for delete an employee, and we'll specify a string maybe by their first name or their address. And we'll say tac U for update. And we could say we could update the employee based on, if we have someone with 120 hours, comma, make them 140 hours. Cool, so we have that, and then also the flags we'll have to have by default are going to be tac F, which contains the file name to our database file, and then tac N, meaning that if a file does not exist already, we're going to create a new database file and then perform some kind of action. So those are the features at a high level, and you're probably wondering why we're doing all of these flags as opposed to, input, output driven stuff like in standard N. When you're writing a database utility, or when you're writing a Unix utility of any kind, it's really important that you don't depend on back and forth over standard in and standard out, and instead make your program based on flags. And then maybe when you're running your program, you have one major read from standard in and then one major write to standard out. But you don't want to have a bunch of prompting and back and forth, because what happens there is effectively, if someone wants to interact with your program and maybe script with it, for example, it becomes very complicated to understand like what to expect, right? So for example, like instead of doing the flag system, if instead we had like a prompt where we had like a caret and then we said input your choice, right? If someone wanted to programmatically use this utility, they'd have to write a script that would look for this string, wait for it. It's called pexpect, right? And then from there, they would have to put in the proper thing. And then like making programmatic use of this tool is very difficult if you do it like this, as opposed to if you do it the other way, where you use flags. You can write a bash script that automatically just uses the tool as intended on the command line, and it makes it much easier to use. So now let's get into the design of this tool. This first part, which is writing this actual, command line parser. We're going to use the get_opt library to do that, and we're going to start in the next lesson. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero2Hero Programming. So today we're going to be working on the employee database. In particular, we're going to be writing the functionality that enables you to supply command line arguments to your program. And then from there, based on what command line arguments are set, we'll be building out the additional functionality like adding an employee, updating an employee, removing an employee, etc. So the way that I have it structured right now is how we talked about multi-module programming in the previous section, right? So right now I have a bunch of folders. I have the final project, that's the top level, like the root directory of the project. I have the bin folder, which will have all of the output binaries, so the final dbview program. I have the include folder, which will contain all of my .h files. I have the make file, which will serve as the main build system to assemble all of the code together. I have the object folder, which contains the intermediate objects that will be compiled in the intermediate stage of our make system. And then the source folder, which contains all of the code that we're going to write here today. We'll ls source. And I've got three main files. I have file.c, which handles file IO, opening a file, closing a file. Main.c, which will be like where the main function lives and some utility functions. And then the majority of the code is going to go into the parse.c functions. This will be responsible for taking the data in the database file, parsing it, and then expanding it into the employee structure in memory, and then collapsing it back into the file at the end of program execution. Also, an important thing to be aware of is I have my make file set up where the new default rule is the run rule. What the run rule will do is it will clean out the system, so it'll remove all the intermediate objects and the bin files. It will run the default rule, which will build my target, and then it will run the target, right? So as I'm going through my my build process here, what I'm going to end up doing is adding tests, right? So eventually we'll get to a point where I can specify a file path, right? What I can do in my make file is I can add that flag to the run, and I can say, the file path I want to use. And over here in this other pane above my head, I can type make, and this will, like I said, delete all the stuff, compile my project, and then run my code with the tests that I specified. As we're going through the code, we want to make sure that our features are doing what we think they do and doing them safely and not crashing. Obviously you should be doing more, I think, thorough unit tests and security tests in your code as you're going through, and that'll happen in a new course that I'm working on. But for now, what we're going to do is just use this as we add features. We'll test those features in our make file, and every time we think we're like at a good stopping point, we'll run make and just kind of see what happens, right? So we'll delete that test for right now and just show that it reflects in the make process, and we'll go from there. Great. So now what we're going to do is, like I said, we're going to go into main.c, and we are going to add the functionality that allows you to check for command line arguments, right? And so there is a good library for this called get_opt. And the way get_opt works is you create a variable to contain the current case that you're on, right? We'll talk about that in a second. And we'll say while c is not equal to, or while c equals get_opt, and it takes argc, argv, and then our command line string. So we're going to say for now that we want to have two flags. We're just going to use these to test. So the first flag will be a Boolean flag that's either on or off. And the way we specify a Boolean flag is we just type it, right? So the tac n flag is now able to be there. And then also we'll have another flag that's f, the file name, and this will take a string. The way we specify that it takes a string is by putting a colon after the flag. So tac n and tac f. So now if the output of that is not equal to -1, that means we're not done parsing all the things. So we'll keep going, right? If it does equal -1, we'll break out of this loop and then go execute the rest of the functionality of our program. So this little while loop here is just reading the command line arguments. And then so what we need to do is, it sets C equal to the current flag that we're working. And now we need to switch on C. So a switch statement is effectively, we're going to, based on the value of C, do something, right? So in the case that the current flag we're working on is n, we have to do something. We have to provide some kind of code to run when this happens. So we'll set some bool called new file equal to true. And I have to declare bool new file equal to false by default, just to have it there. And then I'm also including standard bool.h just so you can see that up there. All it does is essentially create a new type called bool, which is a character that can only be true or false, and internally that's just 1 or 0. So in the case that we see an n in our command line flags, we'll say the new file equals true, and then we'll break. Otherwise, what we can do is we can say if the case is f, we can say that we have some file path variable, and that's going to be a character star file path, and by default it's null. Always good to set those to null by default. And now instead of it being null, we're going to set it to this internal variable that get opt tracks, which is called opt-arg. And at the time that this code runs, opt-arg will contain a pointer to the value on the command line, right? So if I say tacf myfile.db, now the file path will point to myfile.db, so we can use that to open the file in the future, right? And then in the case of something else, we'll say, we'll printf unknown, we'll do unknown option %c. We'll do tac in front of that, and we'll put C here, and then we'll do break. And then the default is that if we somehow get to a case where it's not an unhandled error, we'll return -1. Like this should never happen. We'll just break out of the loop. And then from here, we'll delete this later, but just to prove that our code works, we're going to printf new file is either 0, or we'll say that it's a decimal value, and we'll print that out. And then we'll print the new file flag. And then also we'll printf the file path %s, and we'll print out file path. Okay, cool. So we have that all set up. Let's see if we can run our program and get some command line arguments to it. So we'll type make here. Cool. So we ran the program. By default, new file is 0 and the file path is null. Good. So now what we can do is we can run our program and see if we can actually specify some stuff. So if I put tac n in our program, what happens? New file turns to 1. Awesome. And if I type tacf and I say, my database.db. Cool. So new file is 0. File path is set to my database.db. Very, very good. So now what we have here is the scaffolding for, as we're adding to our code, every time we want to add a feature, all we have to do is add a flag to our switch statement into our argument command like parser here. And then later on in the code, we have to handle if, the logic based on that. So what we're going to do right now is basically we want to make sure that the flag, the file path argument is a required argument. So if we get to the point where we are parsing our code, we're parsing our arguments, and the file path is still null, if file path is still null in this case, we want to do is printf file path is a required argument. We're then going to write a function called print usage, and I'll show you what that does here in a second. And then we're going to return 0. Okay, so we're going to write the function, print usage right now, print usage, and all that is going to do is print the usage. So we're going to printf. Oh, actually, it has to take argv as an input. So we'll do char argv, and then we'll pass argv in the input. And what this is going to do is print our standard Unix usage string. So we'll say usage, it's going to have argv1 as a flag here, and then I'm going to give it all the available flags that we can give our program, as well as a description of those flags. So for right now, all we have is tac n and then tacf file path, or let's do database file. Okay, we'll print that, and then also we'll do printf. So we'll tab out, we'll say tac n, create new database file, and then we'll do printf tab tacf required path to database file. Return 0. And this also takes argv0 as input. Okay, very cool. So if we run this and build this, now what should happen is I got a couple. Oh, I returned 0 in a void. Don't do that. Just return. Cool. So we run the program without a file path. And now it says a file path is a required argument, and it gives us the usage, which shows us how to use our program. We use tac n to create a new database file. We do tac f, which is required to specify the path to the database. Awesome. So I hope you understand how getOpt works and how getOpt is now enabling us to create command line utilities. And what we're going to do in the next lesson is, based on the flags new file and new path, do some logic to figure out if the file exists or not, and then use that to either open the file or create the file. We'll get into that in the next lesson. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgrammer. In our last lesson, what we did is we took a empty C file, right? And we wrote a pretty cool program so far that what it's able to do is when you run it, it parses out the input you give it on the command line, checks for certain flags, and takes certain actions based on those flags. And now what we can do is we can take that flag parsing logic, right? And we can add functionality to it that based on what flags are set, we can take certain actions. And here we did that. We checked to see if the file path flag was set. And if it's not, we say, hey man, we need the path to the database. We throw an error, we leave the program. Now what we're going to implement today is the creation of the database, file itself, right? So we have to take a couple logical steps to do this. And the first one is going to be, we have that tac end flag. So if the new file flag is set, we have to specify we need to write the code to actually create that file. And what we're going to do is we're going to have a function called create database file, and it's going to create the database file at the file path, right? Because we have this variable now, we've confirmed that it's not null. And at this point, we're going to set it, we're going to send it to the create database file function. And what that function is going to return is the database file descriptor, right? So we're going to take that database file descriptor and we're going to have it be a variable in the scope of the main function. So we'll say int database file descriptor, and we're going to set it to -1 by default so we don't accidentally use it as a valid file descriptor. And so this whole, an int comes out and then paths go in, or, structures go in and out, is going to be how all of our functions work. You could do a different function scheme, or maybe your function returns a pointer and you check the pointer, but if the pointer is -1, that's an error case. I don't want to do that because it makes variable casting and checking your errors very painful. What we're going to do here is basically every function we write is going to output some integer, either a good state, a bad state, or a value. And then the inputs and outputs are going to happen in the parameters, right? So for example, if the internal functionality of a function we write allocates a malloc pointer and we need that pointer later on in the code, we're going to pass a pointer to this function, and it's going to overwrite that pointer with the new pointer, right? And we'll talk about that when we get to actually inserting the database header to this file. So, but for now, we have this functionality that if we specify that we have a new file, we need to create a new file. So we're going to go into a different file called file.c, and we're going to write that functionality right now. So file.c, and we're also going to look at the header file. So I already wrote the header file for the file functions just to make it simple. But this is a scaffolding of our project, right? We're going to have two functions, one called create database file and another called open database file. This is going to be used in the case that the file already exists. This is going to be used in the case that the file does not exist, right? So what we'll do is we'll define that function. We'll do that by yanking this, going into the other file and printing that, and then we'll go like this. Cool, so that's our function. What we have to do is we have to say, int fd equals open some file. We're going to open the file name. We want to open it as read write, and we want to open it in create mode. We want to open it with permissions 0644. That's octal. We, as the owner of the file, get to read and write it. Others can read it, and people in our group can read it, and others can also read it, but nothing else. Right? And then obviously, like any other good function that we use, we want to check the return value. So if fd is equal to -1, we p-error on open, and then we return, we have this magic value that we created in our common header file. It's going to be called status error, right? So instead of returning -1, we were just going to use the word status error, and then all other functions will know what status error means because they include common.h. So we're going to return status error. Great. So there is a little bit of a logic issue though here, right? So we'll return the fd, and that's fine. But we want to, create the database file if it does not exist. Well, we're not checking here if the file already exists. And what could happen is that we don't want to let the user of our program think that a database file does not exist, open one that already exists, and then completely wipe it out, right? So instead of what we're doing here, we're going to first try to open the file, int fd equals open file name, read only, and we're not going to specify the create flag or permissions. And this should always fail because the file name should not exist. But if fd does not equal -1, meaning that the file does exist, we're going to say, first of all, close the file. Second, we're going to say printf file already exists. And then we're going to return status error. There we go. So effectively, try to open the file read only and don't create it. This should fail, but if it doesn't fail, close it and then say, hey man, this file is already here. What are you doing? And then continue on by then finally opening that file with the create flag to now make it, open it in read-write mode for us. And then if that somehow fails, tell us why, also return status error, and then return fd. And then we're going to create the functionality for if the file already does exist and we don't specify the new flag, which is going to be, like I said, our OpenDB. And that OpenDB file is going to do the same functionality as the rest of the function, as the previous function, but we're not going to be creating the flag. We're not going to be creating the file. There we go, and return the fd. So there we go. This is the file functionality where we're going to just be opening the file and creating it if we specify the tag end flag. So let's go implement that in our main.c. So if new file is specified, we'll set the dbfd, which is created up here, to some, to the return of this file, of this function. If dbfd still equals status error or -1, we'll do p error. Oh no, we'll just say printf unable to create database file, return -1. Great. And then otherwise, if new file is not spent or is not set, dbfd equals open database file. Same thing on file path. And we'll do the same thing. We'll check the output of that. Print this, and we'll say unable to open the database file. Return -1. There we go. And that's it. So now we can check if this functionality works by adding some tests to our make file. So let's do that real quick. We'll say tab new make file. There we go. So we'll do target. This will show us that the menu functionality works. We're going to ignore this one because we know that it works. We'll do tac f my new database.db. This should fail because the file does not exist. So let's build this. I had an error. Oh, create. No, it's creat. There's actually fun lore behind that. We'll talk about that maybe in a later lesson. Build this. Great. So our program failed. It stopped the build process. So we tried to open the my new database file. Open failed because that file does not exist. Unable to open a database file, and the program returned -1, which is error 255. Perfect. So now let's go through and we'll add the tac end flag to this. This should tell the program, hey, I want to open this database file, and if it doesn't already exist, make it. Try it out. Perfect. So we got the file path set, the new file set, and in theory, if we ls here, it created the my new database file. Now, if we run make again, this should fail because it should try to open our database file, and it should tell us, hey, this file already exists, and then return -1. So let's make again. Interesting. So again, we are not going to get our code right every time the first time. We are going to have errors. We are going to find things that don't work. So let's go figure out what happened here. Let's do some on-the-fly debugging. So if we open the file name read only, if it does not equal -1, let's try to open this read write. Oh, we have to specify create. Actually, no, that's not correct. We have to go and delete the create flag and actually make a test in our make file that tests this. So if we do this line, we can make the new file. But then if I run the same line twice, I should get the file already exists error. So let's do this. Yeah, so the first time we run this, we make the database file, run it again. It says, hey man, that file already exists. And we go from there. Okay, awesome. Just wanted to make sure we had that right because it was not working the way I thought it did. Okay. If they give us the TAC-F flag, we specify the file path. If they say the N flag, we use that to create the database. Otherwise, we open one that already exists. So in the next lesson, what we're going to do is we have the database file itself, right? But right now, it's just an empty file on the disk. We have to go forward and add a header to that file, which will contain metadata related to the current version of the file spec they're using, maybe how many employees it contains, and a magic value that will tell us as the file parser if we even have to deal with this file. Like, is this even a database file? I don't know. The magic value will tell us. So take this code, write it, and get it to work, understand it, and then move on to the next lesson where we'll do a little bit of header foo in our code. So we'll see you there. All right, bye-bye. Hey guys, what is up? Welcome back to your next lesson in Zero2HeroCProgramming. In our previous lesson, we got to a pretty cool place where we can actually use our program. We'll do bin dbview. We'll make a new database file at my new database.db, and we'll say TAC-N. And what'll happen here is it'll make a new empty database file for us. And if we try to do that again, try to run it twice, it'll say, hey man, that file already exists. We can't do that. But instead of doing TAC-N, we can just do TAC-F. It now opens our database project, and we can go and do things with the database file. So the issue here, obviously, is that the database files are empty. They don't have any information, any interesting data in them. So if you look here on the left, on the code piece, I've scaffolded out in our parse.h header file all of the necessary structures we need to actually add important information to that database file. Don't worry about the employees for right now. You know, that's going to happen in a couple sections ahead of a couple sections in the future. But today we're working on the actual header structure, right? So pretty much in any binary data format, the binary data format is first going to have a header that does a few things. So first of all, it's going to have a magic value, and here it's LowLevelAcademy D, or LLAD for a database. It's going to have a magic value that tells the parser basically, hey, is this even a file that you're allowed legally to deal with? If you point this program at like an Excel sheet, for example, it's not going to know how to parse it. So this magic essentially tells it, hey, like this is a good file. The next value is going to have a version, which is going to say basically, hey, we are on version 1 of the file spec. Maybe in version 2, we add a breaking change where we include not only employees, but we also include maybe contractors, or we include maybe managers that we don't account for in this version. So if we find that we try to process a version 2 database in a version 1 program, we won't be able to do that, so we throw an error. And then count in the header. So effectively, the count is going to tell us how many employees are currently tracked in that database. And we'll use that count internally to determine how many employees we're tracking and how many to write out to the database at the end. And then finally, file size, right? We want to track the size of the file in the header because we want to make sure that we're not corrupting the database in any way, and that when we open the file, we want to make sure that the file size in the header is the same as the file size tracked by the database. And when we go to write it to the disk, we're going to use that to confirm that none of our data got corrupted while we're writing it out to disk. So let's go ahead and write out the create database header function and the validate database header function right now. So like I said previously, these function prototypes are going to be pretty much the same way in every function that we write. We're going to return some status value, like a good value, a bad value, or maybe a file descriptor, for example. And then we'll take in our input. And then when we have output that we want to give to the outer program that called the function, we'll pass a pointer. So what's going to happen in either of these is that we are going to either create a header for a new file, or we're going to validate the header of an already existing file. And like I said in the first lesson of this section, the whole way this program works is it has a structure on disk. We read it off disk and parse it out into memory. We then edit it in memory and then write it back down to disk. So what we're going to do in both of these functions is create an in-memory database header structure based on the information on disk or on a new database that we write. And we're going to write it out to the main function so other functions can use that header, right? Because if we want to update the employees that we have to increment the number of employees that are in the header. So let's go ahead and add the functionality for create database header. Right now, we're going to start by yanking this prototype here, and we're going to add it to our parse.c file. So we're going to go ahead and open that. We'll do open parse.c, and this will be the first function that we write. Put it right there. So to create a database header, we're going to add an instance of the structure struct db header t. So we're going to say struct db header t. Header is the name of it, and it's equal to 0, right? And this is going to set all the fields to 0. And then what we can do is we can just start by creating the values in the header. So the version is going to be 1. The header.count is 0. And again, remember, this is a new header file. So this is in the case that we have the new file specified. We're going to use that here to create an empty header for this new file. If we have a file that's already existing, we're going to use the validate header when we write that in the future. So we have header.version, header.count. We'll say header.magic is equal to whatever our magic value name was, header magic. And again, this is going to represent LLAD, or Low Level Academy database. Paste that here. And what is our final field here? Oh, header.file size. We're going to say that currently is equal to the size of a database, or the size of a struct database header t, right? Because that's all it is. Like, the file is only this big. Now, the problem with writing the code this way is that currently this header structure is on the local stack of the create database header function. We want the main function to eventually receive a pointer to this header and be able to pass it around and use it in future functions. So what we have to do, instead of calling header this, where it's a locally defined structure, we're going to actually make header a pointer, and the pointer is going to be the call to calloc, where we're going to allocate one member that is the size of a struct database header t. The reason why this works is because we're able to ask the heap to give us memory. We get a pointer to that memory, and then we can return that pointer out of the function by setting header out equal to that pointer. So we have to modify now the notation for our structure modifications, because when you modify a structure that is a pointer, you use this arrow notation here. This arrow notation, not error notation. And then we also want to check to make sure that our calloc does not fail. So we'll say if header equals -1, we'll say return status error and print that malloc failed. Malloc failed to create db header. Great. And then so now we have our header created, all the values are set. We need to just output to header out. So the thing pointed to by header out is equal to header. What that effectively does is that writes the pointer that we got from calloc outside of our function so somebody else can use it. And again, we could return that value by the return, by the return expression. But the problem is we want to return not the pointer, but a status. And we'll say return status good. No, status success, I believe. We can go look at common.h to figure out what it is. Status success, good. Awesome. So now let's go put that into our functionality here. So in the case that we have a new file, we need to create database header. It takes database file descriptor as input, and the output is going to be the address of the database header pointer. We have to declare that, right? So we're going to have a struct database header t pointer called header, and it's set to null. And again, this pointer will be used to point to the header that comes out of this function, right? So we're going to overwrite that with the functionality in that code, right? So, and then we'll also say if this does not equal status, we'll say if it does equal status error, we'll just say printf failed to create database header, return -1, right? Something went bad, something failed, maybe malloc failed, maybe something else failed, return -1. Awesome. So we have created a new database file, and then locally inside of our program, we have a new database header, right? So we have both of the things needed to effectively create an empty database file. Very cool. We haven't written that out to disk yet, but that'll all happen at the end when we write our output file functionality. So cool. And then in the event that we already have the database file, we're just opening it now, we're not creating it, we now have to write the validate database header function. And so what's happening here is we're going to look at the header file real quick. And we're going to say we're going to copy the prototype here. And we'll print this out like this. And what we're doing here is just taking a file, right? We're going to read the database header out of that file and put it into that structure we talked about before and return that to the user just like we did in the previous function. But now we have to also make sure that all of the fields reflected in the header are valid. If they're not, then like we can't use that file, right? So what we have to do is first do if fd equal or is less than 0, meaning it's an invalid fd, we say printf got a bad fd from the user and then return status error, right? Otherwise, what we're going to do is we're going to create room for our database header on the heap, just like we did before. Database header t pointer header is equal to the same thing, calloc one member of database structure size, right? And then again, if header is equal to -1, printf malloc failed to create a database header, return status error. Great, so we have that. Now what we have to do is unpack the database header, right? Because originally what we did here is we just set our header values equal to some numbers, right? Before we write this to disk, what we actually have to do is essentially set the endianness of the values to be network endian. If you don't understand what that means, all it is, when we have numbers in assembly, if I have a long integer, the integer looks like this when we're talking about it in decimal, right? It's 00, 00, 00, 00, 0, 1. But when this gets actually processed in memory, depending on what's called the endianness of your architecture, it may be different. On a little endian system, on disk, it'll look like this. It'll look like 0, 1, 0, 0, 0, 0, 0, 0. And this is problematic because now if I send this value to a system that is big endian, which is not little endian, it'll think that it means a different value. So it's good practice that when you're dealing with any kind of binary data, you pack that data to be, it's called network endian or big endian on disk, and then you input it, you suck it up, and you process it and set it to what's called host endianness or the endianness of your system. If you don't understand what any of that means, that's okay. Just go along with me for a little bit. What we have to do is first read from the file descriptor to the header pointer the size of a struct database header t. So what it's going to do is going to read all the data out of that file into our structure. And we're also going to say, if this function call does not equal the size of a struct database header t, we need to printf, hey man, p error read, something went wrong. We're going to free the header and return status error. Okay, cool. So if we have the data read in to the header pointer, we now have to do what's called unpacking that data. So like I said, it should be on disk when we write it in network endianness. So we need to unpack it to host endianness. And there's actually a bunch of cool utilities in Linux C that already exist to do that. So for example, we'll say header version equals, this is called host to, or it's called network to host. And is this a long or a short? I forgot. The version is a short. Network to host short on header of version. Effectively, all this does is takes the value of this location, unpacks it so it's stored in the right order that our processor knows how to understand, and we're putting that back in the header in memory so we can deal with it. And when we go to write it to disk, we'll put it back to the original order. So we'll do the same thing for the header count. Header count equals network to host short on header count. Great. And then also we need to do this header magic is equal to network to host long for header magic. And then finally, what is it? Header, header file size. Header file size equal to network to host long for header file size. Awesome. Very, very cool. And now what we can do is, now that all the values are read out of the file system from disk, they're in this header, they're unpacked to a number value that we can understand, we can do our checks. So we could say if header version is not equal to 1, we could say printf improper header version free header return -1. And we could take all of this, we could literally copy and paste this. So we could say if header magic is not equal to header magic, right? Improper header magic, free header return -1. And then we'll finally we have to do our fstat, right? We want to check to make sure that the file size of the file of the file size of the database is equal to what the file size actually is. So we'll call fstat on that. So we'll say struct stat dbstat is equal to 0. We'll call fstat on the fd to the dbstat structure, and we'll say, if header file size is not equal to dbstat.st size, we'll say printf corrupted database free header return -1. Very, very good. So again, this is going to fail initially, right? Because right now, when we run our database function, we are not writing anything out to a disk. So if I compile this and build it, db header, create db header. Sorry, I'm looking for the error here. Got an error at db header. This is struct. Oh, it's no. What's the issue here? File parse. Oh, db header t. db header t is going to be called db header. There we go. Perfect. So now we have to write some tests, right? So we're going to create a new database file called mynewdb. And then what's going to happen is it's going to try to open mynewdb, and it's going to fail because there's no data in the database. Didn't fail. Oh, we didn't actually call the validate function. Yeah, we have to say if validate db file or db header on db file descriptor, and it points to db header is equal to status error, say printf failed to validate database header return -1. Read success failed to database. Okay, interesting. So let's see here. Something went wrong. Oh, because it's 0 bytes. It's not having an error, right? It successfully executed the read. It's just it got to the end of the file. So we could just leave this the way it is. It's probably fine. So we need to actually do now is when we make a new database file, we have to write the output file functionality that will actually output our file to disk, right? So to output our database to a database file, we're going to write a new function that's going to be called void output file, right? It's going to take an fd, it's going to take a struct db header star, right? A pointer to a header, and no employees for right now. We'll deal with that in the next section. But what will happen here is we're going to output the database header to a file when we make a new file, right? So we're going to take this, we're going to put it in our parse.c functionality. And very good. So again, we're going to take the same functionality. If the file descriptor is bad, be mad. Otherwise, we're going to call this db header. So like I said before, right, we have the header structure in memory, right? And the memory is currently tracked as what's called host endianness. We need to now pack it to be network endian to put it onto the disk. So we're going to say that db header magic is equal to host to network long on db header magic. db header file size is equal to host to network long db header file size. We're going to say that db header count is equal to host to network short, because that's a short value on file size. And we're going to say, and not content, count. And then db header, what's the last one? I'm trying to think about it. Version. version is equal to host to network short db header file size or version. Great. So now what we have to do is bring effectively what's called the cursor in the file back to the front of the file. Because we have a file open, we've read the entire file. If we were to try to write to this file, it would just write it at the end of the file. So what we have to do is do this thing called lseek. I'll bring up the man page for that. Do man lseek. And what lseek allows you to do is move the file offset of the current open file to a position, right? So I'm going to seek set, which means I set it to a absolute offset of 0. So I'll do on the DB file at offset 0, set it to seek set, which will move it all the way to the front so we can actually begin to write the database file out. So we'll do lseek fd, do seek set and set it to 0. No, do 0, seek set. Awesome. And now I could do write to the file descriptor. We're going to write out all of the data at db header. I'm going to write out size of struct db header t. Very good. We'll return, and that'll be it. So let's go see if when we make a new file, this actually works. So we'll change our test to just create a new database. Oh, I need to actually call the function. We'll do output. What did I call the function? Output file. Output file to database file descriptor, and it takes a database header pointer as input. Very good. So let's go ahead and make this. Okay, so we ran the file. We still have our flag set. We called our function. Nothing crashed. So let's xxd that file. And very good. So we got the magic is here. We read that it is version 1. There are no employees there, and it is C bytes long, which is 12 bytes long. Okay, very good. So I think we're in a good spot right now. Let's try to run our program on this and just open it by passing it in as a command line flag. Wonderful. It crashed. Okay, so let's figure out what happened here. Oh, it's funny. All right. Always good to have crashes. Always good to have these errors because it shows that we're all human. We'll run GDB on this and do run real quick. I don't know. Do GDB tag args. Continue, run. All right, so we're crashing in output file. Oh, right. So when we actually validate the header here, we are not outputting it to the, we need to do star header out is equal to header. Otherwise, we're not gonna, there's nothing for it to write. It's gonna crash. Great. Okay, that should fix it. We'll make again. We'll run our same test. And there we go. Okay, cool. So this is amazing, right? So what we're doing is we are making our file. Our file is getting output to disk with all these structures in place. And now what we can do is we can run our program. We can open it, and it just did all this validation to make sure that it's a valid database file, and nothing went wrong. We have the header magic check. It checked to make sure that the magic value was there. It tried to make sure that the version of the database is equal to the database version 1. And then it also checked to make sure that the file size reported inside the header is the same as the file size on disk. And if all that passed, it passed it back out to our main function. And our main function will eventually do some additional processing here. But then what we did is we output that file back to disk, and nothing went wrong. The file is still in a good state. And we could run this over and over and over again, and it keeps working. I'm actually going to delete these two outputs here because they're starting to bother me a little bit. But as you can see, we are beginning to get to a place where, we read the database off the disk. We bring it into memory. We unpack it so that we can work on it. We do operations on the file, and then we put it back to disk via our output file functionality. We are in a spot here where we can add any kind of functionality we want to this database. So what we're going to do in the next lesson is write the add functionality where we actually add an employee to the database, write it to disk, and then we can list the database and show all the employees that are in it. So let's do that right now. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. We're at a really cool spot with our project, right? What we can do currently is pretty neat. We can type make on our build system, and we are able to run our project, and it creates a new database file. The database file has a bunch of really cool info, like, the LowLevelAcademy database magic that tells us that this is a file we're able to work on. We have the version, it's version 1. We are currently tracking 0 employees in this database, and it's also a 12-byte long file, which we use all this information to validate that the header is sane, that we're working on a good file, and we're eventually going to use this count to count how many employees into the database we have to read. So in today's lesson, what we're going to do is we're actually going to add the employee functionality, right? So in our parse.h header, I have defined the employee T. So this structure represents the employee that we're going to track in this database, right? So we have their name, their address, and maybe the number of hours that they've worked, right? And obviously, 256 is a random number. It's a good round number that I like to use when I'm tracking buffers. Maybe it's different for you. Maybe you want to make it something else. So that's fine. Also, this will have a lot of dead space in between, the employees. There's a lot of unused space. It's not super efficient. In theory, we could use like gzip compression to compress these employees, but that's not really a topic for today's video. So what we're going to do is we're going to implement the read employees functionality. The read employees functionality is going to take the header as input to specify how many database employees we have to read, because we have that count value. We're going to read it out to an employee database buffer that we create off the heap, which will return to the main function. It'll all come out of the file descriptor for the database file. And if we're successful, we'll say status success. Otherwise, we'll say status error. And then, we'll use that read employees functionality to then add employees or do other things with this employees out structure. This is like the beef and potatoes of this project, because what happens here is we've read the header out of the structure. We've read out all the employees to a list of employees or an array of employees. And now we can do all the functionality we need, like adding the employees, updating the employees, listing the employees that exist just on this structure in memory. And then once we get done editing them, we're going to write additional functionality to the output file function that will output them to the disk. And then we're pretty much done. We're making really good progress here. Let's go ahead and implement the read employees functionality here by putting it into our parse.c. And so same as always, right? If we get a bad file descriptor from the user using our API, we probably should yell at them. We'll go from there. So we need to now figure out what is the count of the users. We'll say int count is equal to, we'll specify that this is the database header, right? DB header, that's the name of the thing. We had the type, which is legal. We just didn't have the name. That's illegal. Now we have a name. The count is equal to DB header, the count. And again, don't forget, at this point, the memory is unpacked to a good usable piece of memory that we unpacked from from network endianness to host endianness. So we have the count. And now we need to create a buffer of space in memory that we're going to use to read off the disk, right? So we're going to say that we'll create struct employee t pointer employees is equal to calloc. We're going to create count elements. So that's the number of elements that are all of size of struct employee t. Very good. And as usual, if employees is equal to -1, we're going to say, hey man, malloc failed, return return status error rather. Cool. Otherwise, now that we're at this point, again, don't forget, we've read the header so far in our previous functions. So the cursor of the file is right where the employees are going to start. So we're going to do read. We're going to read from the FD. We're going to read into the employees structure, and we're going to read the number of bytes that is equal to count the number of employees times the size of an employee. So size of struct employee t. And what this will do is this will populate all of the data into our array that we then can use to do other operations on. Now, again, just like we had to do this with the database header, we had to unpack the database header. We also have to unpack numeric information about the employee. When we store the number of hours, for example, we have to unpack the hours from network endianness to host endianness. We're going to do this iteratively using a loop. So we'll say int I equals 0 for I less than count, I plus plus. And then for every I, we'll say employees of I
dot hours is equal to employees of I dot hours, and we're going to wrap that in a network to host. Is it a long or a short? I forget. It's a long. Boom. And there we go. That's it. We only have to unpack one element there. And then by doing this, what we can do is we can say employees out is equal to employees, and then we could say return status success. Bada bing, bada boom. Very cool. Okay, so we have this, and we're going to call that now in our function here. So once we've gone through, we've either made a new file or validated an already existing file. What we can do now is we can do read employees. That'll come from the database file descriptor. We'll pass in the database header as input, and we'll also pass in a pointer to employees. And employees is now a new pointer, which is going to be a struct employee t pointer employees, right? And we're passing the address of it to the output or to the function because we want to overwrite it with the pointer that comes out of calloc, right? Because we're going to alloc memory here. We want to output it to that location and then return success. And we also have to check that, right? If this does not equal status success for whatever reason, we'll say printf failed to read employees, return 0. Great. Okay, great. So we've made the file, and we compiled it, and it ran, and we're all good. We're getting a couple warnings here. We'll work through these as we get later into the project, but for right now, I want to make sure that these are all good to go. Okay, so now that we have the employees in the database read to some local structure that we can use to modify and create new ones, we have to create a new piece of functionality. We're going to be able to now add an employee to the database, right? So what we'll do to do this, we'll say case A, and we'll say that, we'll call it add string is equal to opt-arg. We'll call break. What we're effectively going to try to do is add the functionality. I'm trying to reset this. Add the functionality where I can do bin dbview on my database, for example. And I want to do tac A for add. And we're going to have a comma separated string that denotes a user. So we'll call him Timmy H. He lives at 123 Cheshire Lane. I don't know. And he's worked 120 hours, right? We'll delete these spaces. But this is what I'm trying to do. I'm trying to build it so that we can add this person to our database. It gets written to the file and stored, and we can open it and view it later, right? Now this will do nothing right now. Unknown option A, we have to add the functionality to process option A. Cool, so let's do that. So we have add string, a new variable, which is going to represent that character string that I wrote out. Nope. It's going to represent that string, the Timmy H Cheshire Lane 120 thing. Yeah, so we'll say that add string equals opt-arg. We'll say char pointer add string equals null. And then cool, so now once we've read out all of the employees from the database, we can now check if add string is set. If add string is set, which means it's not null, this will be true. We can do the add employee functionality. And what we'll do is we'll use the db header and employees as input. Very cool. So what we have to do now is actually implement the add employee functionality, right? We'll do that in our parse.c. So to add an employee, also it needs to take the string as input. Obviously, we need to give it something to add. So we'll pass in add string as input as well. So the add employee will take a struct db header t, db header. It'll take a struct employee t. It's just going to be a single pointer this time. We'll call it employees. We're not trying to output the pointer. We're just trying to read and write data. And then we'll also take a char pointer add string. Cool. What we'll do right now is we will just print out add string and confirm that we've gotten this far, right? So we'll print add string and we'll return 0. Return status success for now. All I want to do is add this to a test in my code. So make a new database file, and I want to do target. We'll add to my new database file tac A, Timmy H, who lives at 123 Cheshire Lane, and he's worked 120 hours. Very cool. Now if I go over here and I type make, what happens? Invalid option A still. Oh, right. I didn't add it to the master list here. This will also have a string. So F colon, meaning F has data, A colon, A also has data. Very cool. All right, do it again. Okay, so what happened here? We made our database file, and then we eventually added database. We tried to add Timmy to the database that called our add employee function, and all that did for now was print the output. Very cool. So now you're probably thinking, okay, cool. So how do we like extract the data from the string? Well, there's a really cool function in C called strtoke. And what strtoke does is you give it a string as input and a string that represents all of the delimiters you want to split that token up by, or that string up by, and it will return a pointer to that first part of the token, right? So for example, if we had our, let's do make again to show you. Make, yeah, okay. So here we have a comma separated string. We can pass this into strtoke with comma as our delimiter, and we will get pointers to Timmy H, 123 Cheshire Lane, and 120, right? So here's how this works. First, what we'll do is we'll do char pointer name is equal to strtoke of add string with the delimiters of comma, right? So the first time we do it, we pass in add string. And now internal to strtoke, there is something tracking how far into the string we are. So to get the next element, the address, we say strtoke null with the same delimiters. What this is going to do is it's going to walk further into the string and get us the next element, the 123 Cheshire Lane. We'll do finally char hours is equal to the same thing, strtoke null, and we'll check the comma, and we'll go from there. And then what we'll do at the end is I want to just print myself all of the values without commas to prove that they were properly extracted. So we'll do name, address, hours. Great, so let's do that real quick. Make, awesome. So we now have the first string, which is the one before extraction, and then we have the second part of the string, which is the string without the commas, and they're all separated into separate strings. Very, very cool. So what we can do with this now is we can actually create an employee structure, and we can add that to the employee structure that we have. So the issue here is that the employee structure is only as long as the employees that were already there, right? So if there were 2 employees in the database before adding Timmy, we now only have room for the 2 employees. What we have to do on this is called realloc, which is a function in C that we pass in a pointer that came from the heap, and we can ask it to reallocate it to a different size, right? So for example, at this point, we have, the count may be 0, right? Now the count is 1, so we need to reallocate that pointer to be 1. Actually, no, what we'll do is we'll handle this outside of the function because I don't want to deal with handling a pointer. I'll go into main.c and I'll say if we call the add string, we will first realloc employees to be size of, we'll do database header of count plus plus. We'll do plus database header count. So what we're gonna do is we'll do this. Ready? Here we go. Sorry, I'm thinking out loud. Database header count plus plus will now increase the count of the employees. We're now going to realloc the size of employees to be database header count times the size of a struct employee t. So now we're going to create room for that next employee, right? So in the case here, if it's 0, it now equals 1. So now we're going to go and we're going to index into that location at the count as the index and copy in all of our data. Great. So we're going to realloc this thing. We'll say employees equals realloc employees to be the proper size. And then we'll go and we'll add that string in our add employee function. Very good. So now what we can do is we can say mem copy. We'll just do this. We'll do stir n copy to employees of database header count -1. It's been added when we need to use it as an index. We'll do dot name. We're going to copy in name. We're going to do the n will be the size of this field, right? Very good. Awesome. And then what we'll do is we'll also do the same exact operation for the address. So adder, sorry, give me a sec here. Adder, very good. These need semicolons as well, obviously. Very good. So what we're doing is we're copying this pointer to here, this pointer to here, and then we're copying just the maximum number of bytes that we can do is the size of that thing. And then finally, what we'll do is we'll say that the employees of this index dot hours is equal to, there's a function called a2i. It converts a string, like, hours right now is a string. We want to convert it to an integer. So we'll say a2i of hours, which will convert that to a number and put it into that array. So there we go. And we'll return status success. Let's try this real quick and see if we can't add little Timmy into our database. Or we're missing a couple of things here. Oh, I'm missing a, two parentheses. There we go. Adder, oh, it's address, not adder, sorry. So address, and size of address. There we go. See, even programmers that do this for a while make mistakes. Great. Okay, so we have created Timmy, we created the database, we added Timmy, we split up the string, and in theory, we copied that into the database. Now the thing is, we have not actually created a way to output this to a file. So what we're going to finally do is in our, let's see here, output file function, which happens in parse.c, we're going to add functionality to output all of the employees to the database, right? So to do this, we have to add a pointer to a list of employees. We'll do that by saying employee t employees. And we're going to now iterate over all of the employees and output them to the disk. So we'll say int I equals 0 for while I is less than database header count, I++. And again, we have to do the thing where we unpack that data, right? We have to say employees of I dot hours equal to host to network long, employees of I dot hours. And then we're going to do is we're going to write basically all of the, or to the FD, the employee structure of I, employees of I. It's going to be the address of employees.I, and we're going to write the size of an employee T, a struct employee T. There we go. And that'll happen for every employee, and then we'll return. Okay, so let's see if we can make this happen. I have an error, output file. Oh, I didn't edit the call. So I have to do output file, and now it takes employees as input. Okay. Make output file, too many arguments, output file, db fd output header employees. What did I mess up? Employees. Oh, I have to edit the prototype in the header file as well. Employee t. It's going to be just employees. It's just struct. Great. All right, let's try it again. Okay, so no crashes, no errors. We'll see if it's actually in the database. But in theory, what happened here is we have, we created this new file. We tried to add Timmy at 123 Cheshire Lane of 120 hours to the database. Let's go ahead and xxd our database and see if it actually got created. It did not. Oh, the issue here is that the db header count has been set to like a magical value because I packed it. So before we do this, we have to say int real count is equal to db header count. We have to preserve it. And then in this loop, we'll say real count instead of the actual count. So let's go ahead and run that real quick, run that test. There we go. So let's try that out real quick and see if Timmy actually got put in the database. He did. Okay, very cool. So see, here you have the database file. We have the header as before. And then immediately following the header, we have the entry for Timmy. So we have Timmy H, who lives at 123 Cheshire Lane. And we have that he's tracked at 120 hours. So in theory, if we keep running this piece of this line, corrupt the database. Oh, you know what? We did not update the file size. So what we'll have to do here is not into the file size. We'll say database header file size is host and network long of the size of a struct database header t plus the size of a struct employee t times database or the real count, which is the count of the number of employees we track, right? We have to put in that like all these things are true. All right, so let's do that real quick. And we'll say, we go like this. We build one, awesome. Make sure that Timmy is still in there. Timmy's still in there, awesome. Now, if I run this over and over again, we should be able to keep adding additional Timmys. And we'll check that out real quick. Yeah, okay. So, oh no, we only keep getting one singular Timmy. Interesting. Oh, for some reason I messed up and wrote that the count is equal to the file size. That's incorrect. Database header count is equal to database header count. How'd that happen? Okay, let's try it again. Great, so now we have Timmy, he should be in there, execute my database. He's there one time. Let's add him a few times. Is he there again? Yes, perfect. So we added Timmy the second time, add him a third time. Let's see if he's still there. Great, so we keep adding Timmy and he keeps showing up in the database. So now we have all the functionality down to add employees to the database. Let's stop for a second, take a breather. I'll let you guys implement this yourselves. Go forth, and we'll add in the next lesson the functionality to list all the employees in the database, and we'll call it there. See you next time. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. We've made some ridiculous progress on this project. If I type make here, what happens is I'm writing our program, which creates a new database file, all based on command line input using getOpt. I'm able to use another flag to specify that I want to add a person to our database. We add that person. We're going to clean up these strings here in a second, and I can inspect the database file, and I can see that they show up in the database. And I can actually run the add function over and over and over again with different people, but the same person in this case, and they keep getting added to our database. So what we want to do now is kind of like prove that this works outside of like XXDing the file. I want to like list all of the employees in the database. So we're going to add functionality to list all the employees by doing it just like we did it for the add string. So we're going to add a new command line flag to our program called L. For list, this is a binary flag or a Boolean flag, so there's no colon required. We're going to have bool list equal false by default. And then we're going to say if case L, we hit the L flag in our program, we're going to say that list equals true. We're going to break. That's going to be it. Awesome. So after we've added our person, if add string is set, we're also going to say if list, we're going to list employees. Bada boom. We're making great progress here. We're going to need the database header and employees as input to that. And this will be a void function. This really should not fail. It's only displaying data. So we'll not check the return from this. And then in our parse.c, where all of our major like file-based database parsing functionality has happened, we'll implement it here. So we'll say that void list employees takes a structure db header t, which is called db header, and a structure employee t pointer, which is called employees. And we'll go ahead and we'll do a for loop, basically, is all this is going to be. We'll say int I equals 0 for I less than db header count I++. And now all we have to do is print the employees, right? So we'll say printf employee, we'll say like the ID, so employee D, and we'll give it the I, it's the current iterator. And then we'll printf with a tab to kind of indent into the screen. Their name is %s. New line, we'll say employees of I.name. And we'll steal this line and kind of paste it a few times. Okay, got a bunch of extra stuff. We'll say address and hours. And we'll say that they live at the address, and they've done %d hours so far. And that'll be it. So let's try this out. Didn't mean to leave that window. Okay, so we'll do our makefile again. Now we have our program and our database with one entry in it. So we'll do dbview TAC-F, my new DB, TAC-L. There we go, employee 0, his name is Timmy H, and he lives at 123 Cheshire Lane with 120 hours. If I do TAC-A, which means we can add another employee, I'll name him, we'll do Kenny G, lives at 444 Wallaby Way, 140 hours, great. And then we'll do TAC-L again, we'll list all our employees, and boom, now we're viewing the database with the employees. In theory, based on this, we can also add a new employee and then list them and then do it again. Great, yes, what we did here is we used the TAC-A flag to add a new employee. They added it here, and then we used TAC-L to view the database. So I hope you understand where we're at right now. Like, we're in a really cool spot where the scaffolding of our program and the organization of our program allows us to add functionality very, very easily. We add the flags here to enable the program to receive the wishes of the user. We parse those flags and set the functionality in the program. And then based on the logic of how we want that to behave, we just add functionality to parse the employee structure and the database header structure, add or remove employees based on what we want, and then write it out to the file here using our output file functionality. So I'm done coding. I'm done coding for you guys for right now. What I want you guys to do is implement this yourself. Take some time, really code this out. This is going to be difficult for you if you're new to the language. I know that, but you will figure this out. You have the pieces. Watch the videos over again. And for you, your homework is to add the functionality to remove an employee by name, right? So what you're going to do is you're going to find an employee by name. You'll find all the Kenny G's, for example, with a TAC-R. You can add an R flag and remove them, and then also add functionality to update the hours of an employee. So find an employee by name and update their hours. Guys, I hope you've really enjoyed this course so far. I hope you feel like maybe you didn't know a lot about C. Now you know not only the C language, but how to build systems or build projects with C. And I really hope to see you in the networking code that doesn't suck course, where I take this project, but we turn it into a network appliance using the POSIX socket API, so we can interact with it over the network using, a command line and tool that allows us to act not just as a database local file parser, but a database service as well. It's been fun, guys. I'll see you in the next one. Take care.